Welcome to Software Engineering. Are you interested in learning about software engineering? Does finding out more about the software building process appeal to you? Would you like to get more information about software development? Does learning about the basics of programming interest you? Would you like to know more about software architecture and design? Or have you ever wondered what the job prospects are like for a software engineer? If so, this course is for you. According to the most recent U.S. Bureau of Labor Statistics report, about 1,850,000 software engineer-type jobs are posted annually in the U.S. alone, and job growth in the industry is projected to increase 22% through 2030. At the time of this course publication, the median U.S. software developer specialist salary is $110,140 annually, and per hour pay is almost $53. Software engineering jobs are also a great way to start on your path to a high-paying career in information technology. This course has 3 instructors, Rav Ahuja, Bethany Hudnut, and Lynn Joyner. Rav is a global program director at IBM and the architect for several IBM professional certificates. Bethany is an instructional designer at SkillUp Technologies, and Lynn is also an instructional designer at SkillUp Technologies. So, what's in this course? It's divided into 5 modules: the Software Development Lifecycle, Introduction to Software Development, Basics of Programming, Software Architecture, Design, and Patterns, and Job Opportunities and Skill Sets in Software Engineering. When you complete this course, you'll be able to describe software engineering and approaches to software development, identify software development tools and technologies, compare different types of programming languages and recognize basic programming constructs, outline approaches to application and deployment architectures, and review the skills required in software engineering and describe the career options it provides. During this course, you will learn through guided instructional videos that walk you through key concepts with essential need-to-know facts, interactive exercises to reinforce what you've learned in videos, insider viewpoints that enrich your understanding of IT support work, practice assessments to help you gauge your knowledge, and finally, graded assessments to prove what you've learned. Upon successful completion of this course, you'll earn a shareable badge and certificate that you can show to prospective employers. We're here to support your success. If you have any questions for the course staff, or if you want to connect with your peers in this course, please feel free to post on the course discussion forums. We're excited you're here, so let's get started. Welcome to Meet the Experts. In this course, you will learn from several experts in various roles who will provide their insights and perspectives about software engineering. Let's meet these experts and learn about where they work and what they do.
Hi, my name is Kadesha, and I currently work as a developer advocate at GitHub.
Hey, well, my name is Liseli Bueno. I'm a software engineer, and I work at Blend, also known as Blend Labs.
My name is Tommy Young. I'm a software engineer at Google. My role is Uber technical lead, overseeing publisher video ads.
My name is Diane Panagiotopoulos. I am a research and development engineer at Bandwidth, and I work directly through Bandwidth. I am not self-employed as like a contractor with them.
Hi, my name is Zubin Pratap. I'm a software engineer and currently I'm a developer advocate at a Web3 startup.
My name is Daniel Rudnitsky, and I'm a full-stack software engineer at IBM.
My name is James Reeve, and I'm a full-stack software engineer at IBM.
Hi, my name is Rupinder, and I work as a Chief Solutions Architect at SkillUp Technologies.
Hello everyone, my name is Upkar Litter, and I'm a developer advocate with IBM.
Hi, I am Jan Stoneman. I'm a solution architect at Smartronix.
Now, let's listen to some of these experts describe a little more in detail about what they do.
Yes, so a developer advocate is a software engineer who enables developer to be successful with a product. That was a mouthful, so essentially what that means is, for example, at GitHub, I create a lot of content. So I will do blog posts, workshops, go to conferences to speak about GitHub, the product. I'll also showcase developers in the open source community and to like give publicity to the projects that they're working on. And being an advocate means that I'm able to communicate deeply about technical concepts in a way that's digestible for engineers across experience level to understand. Before I was an advocate, I worked as a software engineer in the finance sector for 2 years. I spent a majority of my time coding. I primarily worked on the front end of the application using tools such as Git, Docker, GraphQL, React, JavaScript, and the very few times I would go into the backend, we use Node.js on our backend to make changes and updates. My experience as a software engineer and also as a technical content creator paved the way for me to become a developer advocate at GitHub today.
I'm a software engineer right now. I'm still pretty junior, so most of my tasks involve creating new features, fixing bugs, and addressing any customer concerns that we have that they have with the current software.
Yeah, so I work on a suite of products that are they're targeted to large content creators, video publishers, customers such as ESPN, Disney, etc. And we basically have suites of tools to help them monetize their video content, help them distribute it, help them target it appropriately, report on it, troubleshoot it for across all devices, all surfaces. So it's kind of a full suite of products. It starts with the user interfaces that their sales teams and trafficking teams use to sell the ad space, upload the creatives, the advertisements, and target them to their audiences and contextually to the content that that they create. We offer reporting on that, so a lot of it's performance and various other analytics, reach analytics, and so forth.
Previously, before this, I was a software engineer at Google, and before that, I was a software engineer at a small startup. But before that, for about over 15 years, I was a corporate lawyer and then a business executive for a while, and I even had my own startup in the middle. So yeah, very diverse background. And I taught myself to code in my very late 30s when my startup started to fail, and I really needed to keep it going, and my tech co-founder quit. So that's what I do, that's who I am. Today, as a developer advocate, I not only write code, I also produce a lot of educational content and material that is useful for people to onboard onto Web3 and other technologies. And my role is really to help connect the product team with the actual developer ecosystem, bring the two together through code, content, education, and community.
Welcome to What is Software Engineering? After watching this video, you will be able to define software engineering, list the responsibilities of a software engineer, and compare and contrast software developers and software engineers. Software engineering is the application of scientific principles to the design and creation of software. The field uses a systematic approach to collect and analyze business requirements in order to design, build, and test software applications to satisfy those business requirements. When computing began in the late 1950s, software engineering was a relatively undefined discipline, but over time it transformed into a modernized engineering field. The software engineering field became a discipline in the 1960s and evolved as new technologies were developed and the approach to software development became more scientific. Trends in software engineering transformed from ad hoc programming towards more formal and standardized methods. Initially, the creation of software lacked a formal development process. As the world widely adopted computers, software became increasingly integral to more aspects of life. The inefficiencies in the software development process made it difficult to meet the rapidly increasing demand for computing resources and complex software. This led to what is known as the software crisis, which began in the mid-1960s and lasted until the mid-1980s. During this period, software development often ran over budget, behind schedule, and consisted of unmanageable, buggy code. By the time older software solutions came to fruition, newer, better, and faster technologies had already been developed, causing software engineers to have to refactor their code or completely redesign their system. Often software development solutions that worked for small software systems did not scale to large complex projects. Now, some of these issues still exist today, although to a much lesser extent, due to the consistent application of engineering principles to the software development process. Computing resources have become more widely available, and standardized methodologies for software development allow for large complex solutions that scale. The solution to the software crisis involved transforming unorganized coding efforts into an established engineering discipline. The mid-1980s also saw a rise in the growth of computer-aided software engineering, or CASE, which also helped to relieve the software crisis. CASE tools can be divided into 6 categories: business analysis and modeling, development tools such as debugging environments, verification and validation tools, configuration management, metrics and measurement, and project management. Now, the term software engineer is often used interchangeably with software developer, but there are subtle differences. Software engineers are also developers, but the term software developer is usually deemed narrower in scope than that of a software engineer. A software engineer's knowledge is usually broader. Software engineers take a systematic big picture approach in their thinking to software development, whereas developers may have more creative approaches. And both software engineers and software developers have specialized knowledge, but software engineers use that knowledge to build entire systems, whereas software developers use their knowledge to write code to implement specific functionality within a system. Software engineers are often employed on larger scale projects, and they are focused on the broad structure rather than solving an immediate problem. Software engineers are tasked with designing, building, and maintaining software systems. Their responsibilities include writing and testing code and consulting with stakeholders such as clients, third-party software vendors, security specialists, and other team members. The adoption of a measured scientific approach to software development has influenced the way software is created and designed. Today, the development process is typically guided by the Software Development Lifecycle, or SDLC. The SDLC identifies the steps needed to develop high-quality software. Later in this module, we will discuss the SDLC, the traits of high-quality software, and roles common in the field of software engineering. In this video, you learned that software engineering is the systematic approach to design and development of software. Responsibilities of a software engineer include designing, building, and maintaining software systems, writing and testing code, and consulting with stakeholders, third-party vendors, security specialists, and other team members. And finally, software engineers build systems while software developers implement specific functionalities. Welcome to Insider's Viewpoints. What is software engineering? In this video, we will hear from experts discussing software engineering.
I think software engineering is the process of using programming languages and engineering principles to build products. These products could look like web apps, mobile apps, desktop apps, operating systems, or even networking systems. It is a skill that's integral to the success of our modern society because without technology, we couldn't get a lot of things done today. Within software engineering, it's a very broad term. And so within software engineering, you have roles such as front-end, back-end, security, mobile, test, full stack, DevOps, cloud, data, and machine learning. And these are all different types of engineers within software engineering.
I would define software engineering as building and improving software from anywhere from design and architecture to the user interface to fixing small bugs. So anything that falls in that range, that's what software engineers do.
So software engineering to me, I think really has to do with, I consider it a creative process, and it fundamentally is the practice of designing, envisioning, implementing, and then supporting and maintaining software through the full life cycle of it. So not just writing code, but in thinking about the software you're building before you've even written a line of code, the journey from idea inception to actual implementation and launching of said software, and then maintaining it, improving it, supporting it, and potentially evolving it to something else. So it's very much a sort of creative and full life cycle end-to-end engineering process.
I know in the United States, at least, software engineering, software development, programming, they all have, depending on who you ask, they mean very specific things or very hazy things or very contradictory things, or it's like, why do we even have 3 different titles for the same thing? I think of those titles as kind of all meaning the same thing.
What's the difference between a software engineer and a developer?
I think the difference for me, I consider engineering to be a little bit sort of broader, software engineering to be broader than development. I think development to me means is sort of one part of the process. So I think one fundamental difference for me is I think software engineering is beyond just writing code, which I think a developer often is handed a task to write a piece of code, create a module, piece of software, whatever term you want to use. And I think engineering involves sort of starting a very long time before you would even get to the development process, and continues on beyond the time you would actually take your code, deploy it. So this kind of goes into the full life cycle.
In my opinion, there isn't a difference really. So for example, I was trained as a full stack engineer or a full stack developer, but I was hired as a software engineer to work on the front end of the company's application. So I think it's a matter of semantics, and a lot of it I think is a lot of gatekeeping to keep people who don't know anything about the industry out. Somebody who has studied CS may argue differently from I do, but as a person with a non-traditional path into the world of software engineering, I only see it as like title changes and title differences, and I think it depends on what company you work in and what company you work for, because at the end of the day, we're all using the same tools and technology to get the product shipped to production.
I think that they are pretty similar roles. They are used interchangeably a lot, I think. But I think the main difference is that software engineers are also responsible for the system design and architecture, as well as data, how it's received, used, and how it's disseminated, whereas software developers, I think, focus more on the building of apps and features.
So in Canada, being a computer programmer or a software developer is incredibly different than being a computer engineer or a software engineer, where to be an engineer, it means you've taken specific classes in like codes of ethics, and you're held to the same ethical standards as a civil engineer or a mechanical engineer. And so depending on where you are, the titles can mean very different things. And I know for like purposes of immigration, the titles also can mean very specific things, and you have to be careful about like what it is that you put down. But in job descriptions, I kind of see them all used interchangeably, and I tend to just kind of think of them all as the same thing.
It's much of more of a longer time horizon, I think, in terms of engineering versus development. And I think there's a lot more considerations and hats you need to put on throughout the software engineering life cycle versus the kind of more narrowly scoped development cycle.
Welcome to the introduction to the software development lifecycle. After watching this video, you will be able to describe what the software development lifecycle is, explain its history, and discuss some key advantages of using it. The software development lifecycle, known as the SDLC, is a systematic process to develop high-quality software in a predictable timeframe and budget. The goal of the SDLC is to produce software that meets a client's business requirements. The SDLC defines phases of the software development process that encompass their own process and deliverables. It's a cycle of planning, design, and development that can be implemented as an iterative approach to software development. Adherence to the SDLC minimizes risks and costs to the development of high-quality, deployable software. The software development lifecycle began to take shape in the mid-1960s as software development began to necessitate a more detailed approach because of its growing complexity. The SDLC led to a more deliberate approach as large corporations needed to manage complex business systems requiring heavy computational resources. In its initial conception, it used what is called the waterfall method to manage projects where the development of software follows a linear pattern through discrete stages. The SDLC has since been adapted, however, to more iterative methods in response to addressing customer needs and shifting requirements. Waterfall and other approaches to software development will be discussed in another lesson. There are some key advantages for businesses in following the SDLC. The first advantage is that it gives development teams a process to follow rather than using an ad hoc approach to improve efficiency and reduce risks. Secondly, there are discrete phases to the SDLC. Each phase is well defined so that team members know what they should be working on and when. The phases of the SDLC will be discussed in another video. Because of the well-defined phases, it facilitates communication between the customer, other stakeholders, and the development team. The SDLC offers an overview of the process so stakeholders know where they fit into that process. Also, since each phase is discrete, cross-domain teams know when they have completed their tasks and when development can move to the next phase. The SDLC provides room for iteration, where, at the end of a cycle, the process can circle back to incorporate additional requirements as needed. Problem solving is incorporated early in the cycle, so problems are addressed in a timely fashion and can be addressed in the design phase rather than during coding. Finally, each team member has a well-defined role which reduces conflict and overlapping responsibilities. In this video, you learned that the SDLC provides a systematic process for software development. Its initial development in the 60s and 70s was driven by the need for a systematic approach because of the growing complexity of software. And key advantages of the SDLC include a roadmap to the software development process helping to reduce risk and improve efficiency, increased communication between the team and stakeholders, clearly defined and understood responsibilities for each team member, and the ability to be used iteratively, allowing for changing requirements. Welcome to the phases of the software development lifecycle. After watching this video, you will be able to name the phases involved in the SDLC, describe each phase, and identify several tasks associated with each phase. There are generally 6 phases in the SDLC process: planning, design, development, testing, deployment, and maintenance. Each phase is discrete, meaning that tasks from a previous phase do not overlap with tasks in the next phase. The original SDLC was conceived as a traditional waterfall method, where the phases are linear, but have since been adapted to introduce iteration so that shifting requirements can be accommodated. Waterfall and other approaches to software development will be discussed in another video. Note that some organizations may have different names for each stage. For example, planning may be called requirements or strategy or analysis. Also, some organizations may have additional or fewer stages. In the first stage of the SDLC, the planning phase, requirements are gathered, analyzed, documented, and prioritized. When planning a software solution, the following factors must be considered: users of the solution, the overall purpose of the solution, data inputs and outputs, legal and regulatory compliance, risk identification, quality assurance requirements, allocation of human and financial resources, and project scheduling. As part of the planning process, labor and material costs are estimated and weighed against time constraints. Also, project teams are identified and roles of each team member are proposed. If stakeholders are struggling to define requirements, often the development team may produce prototypes during the planning stage to tease out those requirements. A prototype is a small-scale replica of the end product used to get stakeholder feedback and establish requirements. A prototype is used to test basic design ideas. Though prototyping usually occurs during the planning stage, prototyping can occur at various phases of the SDLC whenever requirements need to be reconsidered or clarified as the project develops. After requirements have been gathered, they are combined into a document called a Software Requirements Specification, or SRS document. The SRS needs to be clearly understood and approved by all stakeholders. The developers are also involved at this stage so they can gain a clear understanding of these requirements. Requirements and the SRS will be discussed in more detail in a later video. In the design phase, the requirements gathered from the SRS are used to develop the software architecture. Several team members work together at this stage to design the architecture. The architecture is reviewed by the stakeholders and team, and during this phase, prototypes can be designed. A prototype is a preliminary mock-up of the system or parts of the system used for demonstration purposes. The document created in this phase is called a design document and is used by developers during the next phase, which is the development phase. The development phase, sometimes called the building phase or the implementation phase, is when the developers start the coding process once the design document is completed. The project planners use the design document to determine and assign coding tasks. This phase often requires the use of programming tools, different programming languages, and software stacks. Organizations may also have standards or guidelines that need to be followed. The testing phase is next in the process once the coding is complete, and some large projects have dedicated testing teams. Code needs to be thoroughly tested to ensure it is stable, secure, and meets the requirements outlined in the SRS. Testing can be manual, automated, or a hybrid of both. Product bugs are reported, tracked, and fixed, and the code is retested until the software is stable. Some common levels of testing include unit testing, integration testing, system testing, and acceptance testing. Each of these testing levels will be described in further detail in another video. Next, the deployment phase is where the application is released into the production environment and made available to users. This can also happen in stages. First, it is released onto a user acceptance testing, also called UAT, platform, and once the customer signs off on the functionality, it is released to production. This approach can be used for making software available on a website, mobile device app store, or a software distribution server on a corporate network. Finally, the maintenance phase happens once the code has been deployed into a production environment. This phase helps to find any other bugs, identify user interface issues, or UI for short, and identify other requirements that may not have been listed in the SRS. Code enhancements can also be identified at this stage. If bugs are discovered in this phase that were missed during testing, these errors may need to be fixed for high-priority issues or incorporated into the requirements as part of a future software release, and the process can start over again. In this video, you learned that the SDLC can be divided into 6 phases. Planning involves requirement gathering and development of the SRS. The architecture is developed during the design phase, and the design document is created. The development phase is when coding takes place, and then during the testing phase, issues with the code are found and fixed if possible. Deployment is when the code is released to the production environment. And finally, in the maintenance stage, feedback is collected from stakeholders, other UI issues may be identified, and code enhancements suggested. And this information can be fed into another software development cycle if necessary. Welcome to Building Quality Software. After watching this video, you will be able to list common software engineering processes and describe the common software engineering processes required for building high-quality software. There are numerous processes that are common to software engineering projects. In this video, we will discuss 6 of them: requirements gathering, design, coding for quality, testing, releases, and documenting. The Software Requirements Specification, or SRS, encompasses the process of collecting and documenting the set of requirements that the software needs to adhere to. It may include a set of use cases that describe the business needs and user flows that the software must implement. Software requirements can be classified into 4 broad categories: functional, external and user interface, or UI, system features, and non-functional. These categories are discussed in more detail in another video. Software design is the process of transforming the requirements into a structure that is implementable using code. The software design process translates the requirements into a language the developers can use to write the code. It transforms the requirements into a software solution. The technical lead breaks down requirements into sets of related components with clearly defined behaviors, boundaries, and interactions. These components define the system architecture. The system design incorporates guidance on system functions, performance, security, and platform characteristics. The design communicates business rules and application logic. Application programming interface design, which is how apps talk to each other or communicate with the database, user interfaces, and database design. Code quality refers to the characteristics of the code, including attributes such as maintainability, readability, testability, and security. Quality code must fulfill the intended requirements of the software without defects. Additionally, it should be clean and consistent, easy to read and maintain, well documented, and efficient. Coding for quality entails following a set of coding practices during development. These include following common coding standards, conventions, patterns, and styles, using automated tools known as linters to detect pragmatic and stylistic errors, and commenting in the code itself to make it easy for others to understand and modify. Software testing is the process of verifying that the software matches established requirements and is free of bugs. Its purpose is to identify errors, gaps, or missing requirements when compared with stated requirements. Properly tested software ensures reliability, security, performance, and efficiency. Software testing can often be automated or done manually. Levels of testing include unit, integration, system, and user acceptance. Unit testing is often done by the developer and tests the smallest component of code that can be isolated from the rest of the system. Once components are integrated into the larger product, integration testing occurs. Then, after the larger product is deemed completed, system testing can take place. User acceptance testing, or UAT for short, and sometimes called beta testing, is when the software is tested by the intended end user. Types of testing can broadly be divided into 3 categories: functional, non-functional, and regression. Testing levels and types will be further explained in an upcoming video. When the newest version of the software is distributed, it is referred to as a release. Different types of releases are intended for different audiences. There is generally an alpha, a beta, and a GA release. GA stands for General Availability. The alpha release is the first functioning version of the system released to a select group of stakeholders. The alpha release likely contains errors and may not contain the full feature set, but does contain most of the desired functionality. Design changes may still occur during this release stage. The beta release, also called a limited release, is given to the stakeholders outside of the developing organization. One of the intents of the beta release is to try out the software under real conditions, test the functionality, and identify any outstanding bugs or errors. The beta release should meet all the functional requirements. Then, after beta release, changes are agreed upon, made, and tested, and a stable version is released. The audience for the GA release is all users. Software documentation should be provided to both non-technical end users and technical users. System documentation is geared toward the technical user. Technical users may be other engineers, developers, or architects. System documentation explains how the software operates or how to use it. It consists of README files, inline comments, architecture and design documents, verification information, and maintenance guides. User documentation is provided to the non-technical end users to assist them in the use of the product. Generally, user documentation is provided in the form of user guides, instructional videos and manuals, online help, and inline help. More details about documentation will be discussed in another video. In this video, you learned that requirement gathering is collecting and documenting the set of requirements that the software needs to adhere to. Designing transforms requirements into a structure that developers can use. Coding for quality entails following a set of coding practices during development. Testing is the process of verifying that the software matches established requirements and is free of bugs. There are 3 types of releases, including alpha, beta, and general availability. And finally, documenting requires text or video that explains the software to technical and non-technical users. Welcome to Requirements. After watching this video, you will be able to describe the steps of the requirement gathering process, explain the purpose of a user requirement specification or URS document, explain the purpose of a software requirement specification or SRS document, and explain the purpose of a system requirement specification or SysRS document. Requirement gathering is a 6-step process of defining a problem to be solved and documenting how to go about solving that problem. These steps include identifying stakeholders, establishing goals and objectives, eliciting requirements from the stakeholders, documenting the requirements, analyzing and confirming the requirements, and prioritizing. Generally, the stakeholders work for the organization that requests the development of the software product. Key personnel from the organization may include decision makers, end users, system administrators, engineering, marketing, sales, and customer support personnel. It is good to have a representative from every group that the product affects. The goals of the product should be clearly defined. Goals are broad, long-term achievable outcomes. Goals can include customer outcomes and business goals. Next, objectives should be identified. Objectives are more specific than goals, and they are actionable and measurable actions that achieve the stated goals. The next 3 steps, eliciting, documenting, and requirement confirmation, are usually completed iteratively. Elicitation can be accomplished through surveys, questionnaires, and interviews. As the requirements emerge, they should be documented and checked to ensure they align with the goals and objectives. Documented requirements should be easily understood by stakeholders and the project team. In order to confirm the requirements, they should be analyzed to ensure consistency, clarity, and completeness. And after analysis, the requirements should be shared with and approved by the stakeholders. After confirmation, requirements should be prioritized. Labels such as must-have, highly desired, and nice-to-have are helpful. If possible, order the requirements within those categories. Typically, there may be 3 documents that result from the requirements gathering process: Software Requirement Specification or SRS, User Requirement Specification or URS, and System Requirement Specification or SysRS. The most common of these is the Software Requirement Specification. The Software Requirement Specification, or SRS, is a document that captures the functionalities that the software should perform and also establishes benchmarks or service levels for its performance. Parts of an SRS include a purpose statement that contains the intended use of the SRS, its audience and scope, constraints, assumptions, and dependencies, and requirements which can be sorted into 4 categories: functional requirements, external interface requirements, system features, and non-functional requirements. The product's purpose describes who will have access to the SRS and how they should use it. The scope describes the benefits of the software, its goals, and objectives. And the second part of the SRS should detail constraints, assumptions, and dependencies. Constraints describe how the product must operate under given conditions that may limit options in the design phase, such as conformation to standards or hardware limitations. Assumptions may include things like a required operating system or hardware that is needed by the software to function. Dependencies on other software products should also be noted. Requirements can be classified into 4 categories. Functional requirements are those that cover the functionalities of the software. External requirements are the requirements that address the behavior of the software in relation to external entities, such as users and interactions with other hardware or software. System features are a subset of functional requirements. These are required features for the system to function. There are also non-functional requirements, such as specifying performance, safety, security, and quality standards. User requirements describe the business need and expectations of the end users from the software system. The user requirements are written as user stories or use cases that answer 3 questions. Who is the user? What is the function that needs to be performed? And why does the user want this functionality? User acceptance testing determines if these requirements have been met. Often, though, the user requirements and software requirements are combined into a single SRS document. The SRS details the expectations of the software system. The System Requirement Specification Document, or SysRS, to differentiate it from the SRS, clearly outlines the requirements of an entire system. The System Requirement Specification is often used interchangeably with Software Requirement Specification, but the SysRS is actually broader in scope than the SRS. Many software projects develop an SRS rather than a SysRS. The SysRS contains system capabilities, interfaces, and user characteristics. It also may include policy requirements, regulation requirements, personnel requirements, performance requirements, security requirements, and system acceptance criteria. It also outlines expectations of the hardware needed for the system in addition to software requirements. In this video, you learned that the requirement gathering process entails identifying stakeholders, establishing goals and objectives, and eliciting, documenting, confirming, and then prioritizing requirements. The SRS documents functional, external, system, and non-functional requirements. The URS documents user stories. And finally, the SysRS documents system capabilities and acceptance criteria, and policy, regulation, personnel, performance, security, and hardware requirements. Welcome to Software Development Methodologies. After watching this video, you will be able to list several commonly used approaches to the software development lifecycle, explain waterfall, V-shape model, and agile methods, and compare the pros and cons of each of these 3 methods. There are many ways to approach software development. A specific methodology for developing software is commonly used in order to assist the development team to clarify communication among team members and determine how and when the information is shared. In this video, we will discuss 3 of these approaches: waterfall, V-shape model, and agile. In the beginning, when the SDLC was conceived, it implemented what is known as the waterfall method. Waterfall is a sequential method of software development where the output of one phase is the input for the next phase of the cycle. Development and work on the next phase start only after the completion of the previous phase. All planning, such as defining requirements and architectural design, is done up front. The customer usually does not see the product until it is in the testing phase. For a major version release of the product, the same process is repeated, resulting in long intervals, such as years, between releases. The V-shape model is named as such because the phases form the shape of a V. The phases going down the left side of the V are called verification. Then, going up the right side of the V, those phases are called validation. The V-shape model is like waterfall in that it is also sequential. Each phase in verification corresponds with a validation phase. There are 4 stages that occur on each side of the V. Going down the V are planning, system design, architecture design, and then module design. The bottom of the V is the coding phase. And going back up the V are the 4 phases that correspond to the phases going down the V: unit testing, integration testing, system testing, and acceptance testing. The tests are written during the verification phases on the left and executed during the validation stages on the right. Now, the Agile model is different. It focuses on a collaborative software development process over multiple short cycles rather than a strictly top-down linear process. Agile is what is called an iterative approach to development. It still aligns with the SDLC, but each phase is short. Teams work in cycles, or sprints, which are usually 1 to 4 weeks long. Unit testing happens in each sprint to minimize the risk of failure. Rather than the maintenance stage of the SDLC, the final stage of the sprint is a feedback stage. At the end of each sprint, a chunk of working code is released at a meeting called the Sprint Demo, where stakeholders can see the new functionality and provide feedback. After the sprint demo, the entire process is repeated for every sprint cycle. After several sprint cycles, a minimum viable product, or MVP, is developed so stakeholders can provide feedback on the basic feature set. The MVP contains a feature set to validate assumptions about the software. The 4 core values of Agile development outlined in what is known as the Agile Manifesto are individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. The main difference between traditional SDLC methods, such as waterfall and the V-shape model, compared to the Agile method of software development, is the former are sequential, whereas Agile is cyclical. Traditional SDLC methods, such as waterfall and V-shape, center around the whole product being developed before soliciting customer feedback, whereas Agile focuses on quick, short bursts of development. There are pros and cons to each method, though Agile is probably the most popular method used in modern software development. Regarding the pros of the waterfall method, it is easy to understand and follow. Each stage is discrete and well-defined, making it easy for all team members to understand their roles. Also, since planning is done up front, it is easier than iterative methods to estimate a budget and allocate resources. That said, waterfall lacks flexibility. Since all planning is done up front, if a requirement is changed or overlooked, that change can be hard to incorporate at a later date. Inevitably, unforeseen complications happen or agreed-upon functionality shifts from what was initially envisioned. Like waterfall, the V-shape model is simple and easy to use. It is even more rigid than waterfall, but designing test plans during the verification phase saves considerable time during coding and validation phases. Drawbacks are also similar to waterfall because it does not readily accommodate changing requirements. Once an application is in the testing phase, it is extremely difficult to go back and change functionality. Agile development is different, relying on ongoing research, planning, and testing during product development. When adding new features to a product, development still goes through the same phases as in traditional SDLC. But with Agile, new and changing requirements are handled quickly and easily because planning is initiated at the beginning of each sprint cycle. Most resources are spent on the building phase. At the end of each cycle, the QA team, stakeholders, and the customer have some piece of working code to test against requirements and are encouraged to provide feedback. As coding languages and technologies have developed in recent years, they now allow for modular design where developers can focus on smaller chunks of code that are readily integrated into the larger product. These small chunks can be released to provide the MVP. Cons of Agile are that upfront planning, such as budgeting and scheduling, can be challenging because the overall scope of the product is not clearly defined. In this video, you learned that 3 of the common approaches to software development include Waterfall, V-shape model, and Agile. Waterfall and V-shape are sequential, whereas Agile is iterative. Both Waterfall and V-shape models are easy to implement, but neither accommodates changing requirements well. And Agile allows for changing requirements, but resource allocation can be challenging. Welcome to Software Versions. After watching this video, you will be able to discuss software versions on computing platforms and identify software versions and numbering. Software versions tell us a lot about programs and applications. Users can determine what software version they are using, and developers can provide useful information with version numbers. Software version numbers vary in length and meaning. However, most version numbers follow a similar format and represent similar information. Version numbers indicate when the software was released, when it was updated, and if any minor changes or patches were made to the software. Software versioning is how software developers keep track of new software, updates, and patches for programs and applications. Version numbers can be displayed in several ways. Version numbers can be short or long depending on the software and the preference of the developer with 2, 3, or 4 number sets. Each number set is divided by a period. The first release of an application or program might have a 1.0 as the version number to indicate no updates, patches, or fixes to the software. Note, a version still in beta or testing could have a version number lower than 1, such as 0.9. A program or application with many releases and updates will have a longer number, sometimes 4 different number sets within the version number. Some software developers may use dates for their versioning. For example, Ubuntu Linux version 18.04.2 was released in 2018 April. The third number set, .2, designates an additional change or update. What do these numbers mean? Some version numbers follow the semantic numbering system and have 4 parts separated by a period, but not all numbering systems follow this 4-part example. In semantic numbering, the first number indicates major changes to the software, such as a new release. The second number indicates that minor changes were made to the software. The third number in the version number indicates patches or minor bug fixes. And finally, the fourth number indicates a build number or build date, and it can indicate less significant changes made. Software version numbers are identified in the About or Help section of software. You can practice identifying your version number in a web browser. This example illustrates how to view the version number in the Google Chrome desktop web browser. However, if you are using a different web browser, you should be able to follow the same or similar steps. To view the web browser version, first select the 3 dots or 3 lines in the top right corner of your browser. Next, select the menu item, Help, then select About to view the version information. The version of your web browser will display. Are newer versions of software compatible with older versions? Lack of compatibility between old and new versions of software is a common problem. You can troubleshoot compatibility issues by viewing the software version to determine if you are using an outdated version of the software. Sometimes updating software to a newer version will resolve compatibility issues. Some software is backwards compatible. If a program or application is backwards compatible, then the older versions of files, programs, and systems will work properly with newer versions. In this video, you learned that version numbers indicate the history of changes, updates, and patches to software. Some version numbers follow the semantic numbering system and have 4 parts separated by a period. Compatibility with old and new versions of software is a common problem, and you should view the version of the software you are using to determine software compatibility. Welcome to software testing. After watching this video, you will be able to define the terms functional testing, non-functional testing, and regression testing, and compare and contrast typical testing levels. Software testing is the practice of integrating quality checks throughout the software development cycle. The purpose of testing is to check whether the software matches expected requirements and ensure error-free software. In order to test software, the team writes test cases. These test cases are written to verify the functionality of a software application and ensure requirements have been satisfied. Test cases can be written in different stages of the SDLC and may vary depending on the type of test or the method used to develop the software, such as Agile or Waterfall. A test case contains steps, inputs, data, and the expected corresponding outputs. Regardless of the test type or development method, test cases should always be written after requirements are finalized. Software testing helps evaluate the software to identify whether or not the software product meets requirements and is error-free. Types of testing can be broadly classified into 3 categories: functional testing, non-functional testing, and regression testing. Functional testing usually involves black box testing, which is a method of testing without looking at source code or internal structure. Functional testing is only concerned with inputs and corresponding outputs of the system under test, also called the SUT. It is entirely based on testing functional requirements, and functional testing can be carried out manually or using automated tools. The goal is to test the functionality of the application, making sure the application is usable and accessible. Functional testing tests the SUT to make sure it meets functional requirements. Functional testing makes sure that when user errors or input edge cases do occur, the software handles those exceptions seamlessly by displaying appropriate error messages. Non-functional testing includes testing the application for attributes like performance, security, scalability, and availability. Non-functional testing checks to see if the SUT's non-functional behavior is performing properly. Non-functional testing should answer questions like the following: how does the application behave under stress? What happens when many users log in at the same time? Are the instructions in documents and user manuals consistent with the application's behavior? Does the application behave similarly under different operating systems? How does the application handle disaster recovery? And how secure is the application? Regression testing, also called maintenance testing, confirms that a recent change to the application, such as a bug fix, does not adversely affect already existing functionality. Regression testing should occur when there has been a change in requirements or when defects have been fixed. In order to conduct regression testing, all or some of the test cases should be selected to test against the application. Regression test case selection and prioritization can be challenging and can depend on several factors. Common reasons for regression test case selection include cases that have frequent defects, contain frequently used functionality, contain features with recent changes, or are complex test cases, edge cases, and randomly successful or failed test cases. Now that we have discussed different types of testing, let's discuss testing levels. There are 4 testing levels: unit, integration, system, and acceptance. Each level occurs at a different time in the SDLC. There are 4 different levels in order to reduce the amount of time spent on testing by preventing overlap. We will discuss each of these testing levels next. Unit testing refers to the tests that verify the functionality of a specific section of code, usually at the function level. It is performed by the software developer or engineer during the development phase of the software development lifecycle. Unit testing aims to eliminate construction errors before code is integrated with other modules. Unit testing is intended to increase the quality of the resulting software, as well as the efficiency of the overall development process. Integration testing seeks to identify errors when two or more smaller independent code modules are combined. Integration testing is another type of black box testing. Prior to integration testing, smaller independent code modules that passed unit testing are incorporated into the larger software application. After modules are integrated together, then integration testing can occur. Integration testing exposes bugs that occur when those smaller units of code interact with each other. Integration testing uncovers deficiencies in communication with a new module in conjunction with other existing modules, databases, or external hardware. Integration testing uncovers situations where bugs develop due to differing programming logic between modules, for instance. Also, sometimes during module development, requirements change, and the module isn't fully unit tested. Poor exception handling can cause problems when modules are integrated together. System testing occurs after integration testing and is conducted on a complete integrated system to evaluate the system's compliance with its specified requirements. It validates the system as a fully completed software product. System testing is both functional and non-functional, and system testing is done in a staging environment which should be similar to the production environment. And finally, acceptance testing is formal testing with respect to user needs, requirements, and business processes. It determines whether a system satisfies the needs of the users, customers, and other stakeholders. Acceptance testing is usually done by the customer or the stakeholders during the maintenance stage of the SDLC. In this video, you learned that there are 3 categories of testing: functional, non-functional, and regression. Unit testing verifies small independent chunks of code. Integration testing looks for errors when 2 or more small chunks of code are combined. System testing validates the system as a fully completed software product. And acceptance testing verifies correct implementation of user requirements and business processes. Hello and welcome to Software Documentation. After watching this video, you will be able to list documentation formats, compare and contrast product documentation to process documentation, describe the categories and types of documentation, and explain the purpose of standard operating procedures. Software documentation is information about the software that describes what the product is and how to use it. These can be written, video, or graphical assets associated with a software product's development and use. Documentation can be in any of these 3 formats. Documentation is an essential aspect of software engineering applicable across all the phases of SDLC. Software documentation can be written for different types of audiences, such as end users, software developers, QA engineers, system administrators, and other stakeholders. Documentation can be divided into 2 categories: product and process. Product documentation relates to the product's functionality, whereas process documentation describes how to complete a task. Process documentation should provide the requirements for the quality implementation of a business process. Okay, now let's discuss some specific types of product documentation. There are many types of documentation, and we will discuss 5 categories, including requirements, design, technical, quality assurance, and user documentation. Requirements documentation is written during the planning phase of the SDLC and is intended for the development team, including the developers, architects, and QA personnel. Requirements documentation describes the expected features and functionality of the software system. It includes the software requirements specifications, system requirement specifications, and user acceptance specifications. Design documentation is written by the software architects and the development team to explain how the software will be built to meet the requirements. It consists of both conceptual and technical design documents. Technical documentation includes comments written in the code to help other developers read the code to understand its behavior. It also may include working papers that explain how the code works, and documents that record engineers' ideas and thoughts during project implementation. Quality assurance documentation includes all documents that pertain to a testing team's strategy, progress, and metrics. Types of test documentation include test plans, test data, test scenarios, test cases, test strategies, and traceability matrices. Traceability matrices map test cases to their requirements. User documentation is intended for end users and explains how to operate the software or help them to install or troubleshoot the system. End-user documentation includes frequently asked questions, installation and help guides, tutorials, and user manuals. Standard operating procedures, called SOPs, often accompany process documentation. Process documentation provides an overview of a process, but SOPs go through much greater detail. The SOP is written documentation that explains step by step how to accomplish a common yet complex task that is organization specific. For example, checking in code using a code repository is common knowledge for a software engineer. However, an organization might have specific steps to follow for that organization in order to get code merged into the main branch. The SOP documentation explains those steps in detail. SOPs can be in the form of a flowchart, a hierarchical outline, or step-by-step instructions. Documentation in any form must be kept up to date. Take, for instance, online user manuals. If a cloud-based application user interface changes, then the accompanying online documentation must be updated accordingly. Businesses need to ensure they allot resources for this step. With regards to the software development in the SDLC, updating documentation happens during the maintenance phase. Ideally, documentation should also be reviewed periodically to ensure its accuracy. In this video, you learned that documentation comes in 3 formats: written, video, or graphical. Process documentation describes how to complete a task. Product documentation relates to how a product functions. The types of product documentation include requirements, design, technical, QA, and user. And SOPs are written instructions detailing an organization-specific procedure. Welcome to Roles in Software Engineering Projects. After watching this video, you will be able to list the common roles on a software engineering project, describe each role, and explain the responsibilities of each role. There are several common roles on a software development project, and these roles can have different names depending on the approach being used, such as Agile or Waterfall. Sometimes different companies have different names for similar jobs, but not all projects will have all these roles. The roles we will discuss in this video are Project Manager or Scrum Master, Stakeholder, System or Software Architect, UX Designer, Software Developer, Tester or QA Engineer, Site Reliability or Ops Engineer, Product Manager or Owner, and Technical Writer or Information Developer. Now let's describe each role and some of the responsibilities for each job. Traditional SDLC methods have project managers, but in Agile, the equivalent role is called a Scrum Master. A project manager makes sure the project runs smoothly and facilitates communication about the project. The project manager often deals with bigger picture issues such as planning, scheduling, and budgeting, allocating personnel and resources, executing the software plan, and team communication. In Agile, there is a Scrum Master. Rather than focusing on planning, the Scrum Master is focused on ensuring team and individual success. Remember that the 4 core Agile values prioritize people and communication over processes, and the Scrum Master is responsible for facilitating that communication. The stakeholders are the people for whom the product is being designed. They include individuals such as the customer, end users, decision makers, system administrators, and other key personnel. The stakeholder is mainly responsible for defining project requirements and providing feedback if the team members need clarification on requirements or if a proposed solution cannot be solved as planned. The stakeholders may also sometimes participate in beta testing and acceptance testing before the software is released. The system architect designs and describes the architecture of a project as well as communicates that architecture to team members. They are sometimes also called a software architect or a solution architect. They are responsible for designing the essential characteristics of the inner structure and technical aspects of the software. The architect provides technical support across the different stages of the SDLC. Note, software architecture will be discussed in further detail in another module. UX means user experience. The goal of a UX designer is to balance making the software intuitive, but also as robust as it needs to be to address requirements. They define how the software behaves from the user's perspective. The UX designer determines how the software communicates its functionality to the end user and how the end user interacts with it. Next, the developers write the code that powers the software. Responsibilities include implementing the architecture laid out in the design document, incorporating the requirements laid out in the software requirements specification, and employing the UX requirements determined by the UX designers. Testers, or QA engineers, are in charge of ensuring the quality of the product and that the software solution meets customer requirements. They are responsible for writing and executing test cases to identify bugs or deficiencies and provide this feedback to the development teams. A site reliability engineer, sometimes called an SRE or ops engineer, bridges development and operations by combining software engineering expertise with IT systems management. They track incidents and facilitate meetings to discuss them. They also automate systems, procedures, and processes, assist with troubleshooting, and ensure reliability for the customer. The product manager or product owner has the vision of what the product should look like. They have an intimate understanding of the client's requirements and the end user's needs. They are responsible for leading development efforts to create the software and for ensuring the product provides the value stakeholders are looking for. Finally, the technical writer or information developer writes documentation for the end user. They write documentation on technical material geared towards a non-technical audience. Not only does this documentation help the end user to use the software, but it also helps the customer so they can provide timely feedback to the development teams. Technical writers may be asked to write user manuals, reports, white papers, and press releases. In this video, you learned that there are a variety of job roles on a software development project, and each occupation has responsibilities unique to each role. Welcome to Insider's Viewpoints, job roles in software engineering teams. In this video, we will hear from experts discussing the various job roles you can expect to work with on your software engineering team.
Yeah, so on the engineering team I worked with, we had a product manager, we had a tech lead, we had a few QA analysts or test engineers, and we also had access to UX designers. And so the product manager ensured that we were on task and on track to deliver the features that we said we were going to build according to the business needs. That way we're not left behind.
Yeah, I think in my experience, the roles that software engineers would interact with the most, I think would, in no particular order, product managers. So the folks who are actually sort of working with the sales teams, the marketing teams, figuring out what actually needs to be built, what are customer needs, what are innovations and ideas that, looking forward that you might want to invest in and build out.
We asked our experts to describe these job roles in software engineering teams in further detail.
I think software engineering these days, as it becomes more and more, it's more and more large scale, more complex, more systems at play, more considerations. There's just a lot of things to consider in today's world as a software engineer. So you often work with a project or program manager who helps you set up your timelines, helps you ensure you're meeting your goals, helps you unblock yourself, helps you keep your stakeholders up to date with what is happening with your project. So there's just a lot of pieces involved, and I think project and program managers really are there to help tie it all together.
So the product manager would always act somewhat like a scrum master. So like we would have stand-ups and we would talk about the tickets that we had in Jira, and it was like, okay, so what are you working on? What do you need help with? And are there any issues? And during that process, the product manager does ensure that we were on task and on track, and if we had any issues, he would help us to resolve it.
You'll have a software engineer who's more focused on the architecture, and they can keep the big picture in their brain more easily. And then some software engineers who are more the nitty gritty, I'm sitting down and I am writing code, and my job is to like turn business logic into computer logic. And some companies have those all split out as different roles.
I think software engineers and in these roles, the more they're embedded and work closely together and actually collaborate as part of a single team, versus handing off things in a more waterfall approach. I think that's generally the best way, or one of the most effective ways, is to actually work together as much as possible. Regular check-ins, actually having brainstorming sessions, group chats that involve all the various folks from all the roles. I think close collaboration there is super key.
And at some companies, all the different hats have their own titles. So you might be talking to a software engineer who's actually doing more kind of DevOps, infrastructure building, monitoring and alerting kinds of work. And then there's a software engineer who's also doing QA work, and they're the ones who are focusing on pipelines and continuous development, continuous integration type projects, working on getting test suites and automation all set up.
In terms of working with the UX designer or the UX engineer, they would give me like specific specs from Figma in order to meet the certain specifications of the business. And let's say we're building a checkout page, so the UX designer would design the spec out page in Figma and then deliver that spec to me, and then I would code it according to the design.
UX designers who actually come up with if you are working on and engineering a user interface, you'll work with UX designers to essentially from the moment of sketching out sort of a draft on paper or a whiteboard of an idea, all the way down to working with them on mocks and implementing the mocks and iterating on those. UX researchers often are worked with when you actually need to go out and do research in market and interview your partners or customers to get sort of as real time as possible and just real feedback from real users of your software.
So once I code something, I get it reviewed by my tech lead or my senior engineer. It would go to QA for them to test the application to ensure that whatever I did or implemented didn't break anything. If something is broken that I didn't catch, the QA tester would write up like a test plan or would do like a detailed testing document. That way I understood exactly what needed to be resolved, and I would resolve it and then go back to the QA person and say, hey, this is fixed, can you take a look at it again? And they would tell me whether or not it's fixed and whether or not something else was broken, which often happens with code.
So you generally work a lot with product managers because you need to know what to build. They generally give you a lot of guidance on on what they want to build, and you collaborate with them in terms of how to build it and discuss trade-offs and timelines and expectations. So it's a very much a collaborative process.
Typically, I have found that I interact most with product owners. So either at some places it's been a customer who works inside the company, and so I go to them quite frequently for questions on clarifying refinements, for getting test schedules up and running, for figuring out pain points and trying to optimize their workflows using technology to support them.
Software engineers work often with site reliability engineers, or sysadmins as maybe the role could be called, to actually maintain and help run the software and deploy it and actually get it running somewhere that's not on your desktop. You often work with more dedicated test engineers who are responsible for end-to-end testing, automated testing, integration testing at all points of the life cycle.
So as an engineer, you're never alone, you're never working alone. It's just a matter of like knowing how to communicate directly with the people on your team.
Hello, welcome to Overview of Web and Cloud Development. When you're starting out as a web developer, it can be difficult to determine what you need to learn and what order you should learn it in. Understanding how familiar websites are constructed and delivered to you is a good starting point. Let's review the basics of how you interact with a website. You launch an internet browser. There are lots available. Google Chrome, Microsoft Edge, Mozilla Firefox, and Apple Safari are some of the most popular. The browser has an address bar into which you enter a URL, like www.ibm.com. The browser then contacts the server with the name and requests the information that makes up the website. The server then sends a response, which contains the data that the client requires to display the website. For most websites, the server will return HTML, which defines the structure of the page but doesn't look very attractive, CSS, which adds style and flair to the page, and JavaScript, which adds interactivity and dynamic content. Content displayed by websites can contain elements that are either previously stored on the server, called static, or generated each time they are requested by the client, called dynamic. Dynamic elements can involve information coming from other systems and applications, such as databases. Most websites contain static and dynamic elements to provide the best user experience. Cloud applications are similar to websites in that they request content that a server returns. Cloud apps are built to work seamlessly with a cloud-based back-end infrastructure, cloud-based data storage and data processing, and other cloud services, making them very scalable and very resilient. The environment for building websites and cloud applications is divided into two primary areas, front-end and back-end. The front-end deals with everything that happens at the client side, everything the user can see and interact with. You can choose to specialize in front-end coding using HTML, CSS, JavaScript, and related frameworks, libraries, and tools. The back-end deals with everything that happens on the server before the code and data are sent to the client. The back-end coding usually handles the logic and functionality that make the website or app work, and the authentication processes that keep data secure. Back-end developers may also work with relational or no SQL databases, even collaborating with database administrators in bigger projects. Full-stack developers have skills, knowledge, and experience in both front-end and back-end environments. Whichever way you choose to specialize, you will need the appropriate tools to help you work. The first tool most developers add to their resources is a code editor. Developers also need tools to integrate, build, compile, and debug code. Integrated Development Environments, or IDEs, incorporate some of these additional capabilities beyond just code editing and make it easier to build and manage your code. Good IDEs support multiple languages and integrate with management and storage tools like Git and GitHub. Other useful features are custom extensions and themes for supporting your working style and environment. Examples for code editors and IDEs include Sublime Text, Atom, Vim, VS Code, Visual Studio, Eclipse, and NetBeans. In this brief overview, you learned about the basic communication between client and servers, how websites are built and displayed. Front-end development is about what happens on the client side. Back-end development is about what happens on the server. Full-stack development includes both front-end and back-end development. IDEs will help you create and manage your code. Internet websites offer lots of different services, one of the most popular being online shopping. When you explore an online shopping website, navigating through pages, choosing different product categories, or comparing products, you are interacting with the front end of a website. Let us see how the front end of a website is developed by front-end developers. For this, we need to understand how a website is made. To create a website, web developers usually use hypertext markup language, HTML, cascading style sheets, CSS, and JavaScript. These languages are designed to work in conjunction with each other. HTML is used to create the physical structure of a website. The physical structure contains elements such as text, links, images and videos, page dividers, and buttons. The HTML code ensures a proper formatting of all text and image elements so that browsers display the page consistently. The back-end developer codes the structure of the website. A website is like a house which has only been constructed. Just like we need interior designers to add style to a space, we need front-end developers to add the necessary glamour and appeal to a website. When you order products from any website, you realize that the pages have a pleasing font, attractive colors, and are easy to navigate. Developers use CSS to create stylish websites. CSS provides front-end developers with a standard method to define, apply, and manage different sets of style characteristics for a website and each of its components. CSS ensures uniformity in look and feel, style, colors, fonts, designs, and layouts. So, HTML is used to create the structure, and CSS is used to design it and make it appealing. CSS is also used to create websites that have cross-browser compatibility, which means that they are compatible with multiple browsers and multiple devices, such as PC, mobile devices, iPads, etc. Online shopping websites are intuitive, interactive, and quick to load. This is where JavaScript comes into the picture. JavaScript is an object-oriented programming language that is used in conjunction with HTML and CSS to add interactivity to a website. For example, you use HTML to add a login button to a page and CSS to style that button. Then you use JavaScript to add login functionality to that button. A new front-end development language is Syntactically Awesome Style Sheets, SASS, called Sass. It is an extension of CSS that is compatible with all versions of CSS. Sass enables you to use things like variables, nested rules, and inline imports to keep things organized. Sass allows you to create style sheets faster and more easily. Another language that is being used now is Learner Style Sheets, LESS, or LESS. LESS enhances CSS, adding more styles and functions. It is backwards compatible with CSS. Less.js is a JavaScript tool that converts the LESS styles to CSS styles. Using all these languages, websites are designed as reactive and responsive. Reactive or adaptive websites display the version of the website designed for a specific screen size. For example, a website can provide more information if opened on a PC than when opened on a mobile device. Responsive design of a website means that it will automatically resize to the device it is being accessed from. For example, if you open up a product's website on your mobile device, it will adapt itself to the small size of the screen and still show you all the features. A JavaScript framework is an application framework that is written in JavaScript. Programmers can manipulate the different functions, use them wherever required, and can create device-responsive applications. A few examples of several frameworks being used are Angular Framework, an open-source framework being maintained by Google. Angular frameworks allow websites to render the HTML pages quickly and efficiently. It has built-in tools for routing and form validation. React.js has been developed and maintained by Facebook. It is a JavaScript library that builds and renders components for a web page. It is not a complete suite of tools. For example, routing is not a part of this framework and will need to be added using a third-party tool. React.js only helps build and drop components into a page. Vue.js is maintained by the community, and its main focus is the view layer, which includes user interface, buttons, and visual components. It is flexible, scalable, and integrates well with other frameworks. It is very adaptable. It can be a library or it can be the framework. The task of a front-end developer evolves continuously. The technologies are upgraded constantly, and so front-end developers need to keep upgrading the websites that they create. The websites that they create should work in multiple browsers, multiple operating systems, and multiple devices. Welcome to the importance of back-end development. A front-end developer creates websites and cloud applications using HTML, CSS, and JavaScript to create what the user sees and interacts with in the client software. A back-end developer creates and manages all the resources that are needed to respond to the requests that the user makes through the client. The back-end developer's tasks focus on enabling the server infrastructure, or back-end, to process requests, supply data, and provide other services securely. Front-end and back-end developers must work together very closely. Each needs to understand the requirements of the solution and how their respective parts will interact before the development process can begin. Throughout the lifecycle of the website or cloud app, front-end and back-end developers collaborate to resolve issues and add functionality. How does the work of a back-end developer affect you as you are browsing the internet or using a cloud app? Think about it like this. When you're shopping online, what happens to the data you enter? Your login information, your product searches, your payment info. The back-end processes all of these things, and the back-end developers write and maintain the parts of the application that process the inputs. Let's think about your experience as you explore an online shopping site and make a purchase. As you search for products, your search request is submitted to a web application, which then retrieves the data from a separate database and serves it back to the client for display. To facilitate this, a back-end developer must understand the language that the web application uses, how to query the database for the correct data, and how to bring the two together. Even a simple task like navigating around the site can require the skills of a back-end developer. Many sites have restricted areas that are only available to users who have an account and have logged in. User account management, authentication, and authorization can be the responsibility of the back-end developer too. Once you've decided what you want to purchase, you must add it to your cart and make a payment. The purchase process requires you to submit sensitive information, such as your address and credit card number, and the back-end developer must ensure that this data is securely handled and stored. Front-end client interactions, whether a request for data like an image, accepting input from a user filling out a form, or securing sensitive information like a credit card number, all require different services from the back-end server. Each request needs to interact with the back-end in a different way. Back-end developers use APIs, routes, and endpoints to process incoming requests. An API is code that works with data, usually using JSON or XML. APIs have set rules and structure. A route is a path to a website or page that the user interacts with. Routes generally take user input and show results based on the input. An endpoint may be an API or may simply be a path. When a request from the front end arrives at the back end, it is routed to the correct service. If the back end has an endpoint defined for the request by using routing, the request will be addressed and replied to. If the endpoint is missing, the server returns a 404 error. Back-end developers must create and maintain this server-side routing. Along with back-end APIs, routes effectively allow the front-end client to plug into the correct socket at the back end. APIs provide a mechanism for cloud apps, mobile apps, and other types of software to access resources from the back end. To perform all this back-end development, you will need to be familiar with at least one back-end language and its associated frameworks. Among the most popular languages today is JavaScript, which was originally designed to run in web browsers, adding extra interactivity and dynamic content to web pages. JavaScript is also being used on the back end, with new releases adding server-side functionality. JavaScript has many frameworks, but two of the most well-known are Node.js and Express. Python is another popular language. It's very flexible and easy to learn. Python has wide functionality. It can be used for everything from creating web pages to connecting to a database to performing data analysis. Two well-known Python frameworks are Django and Flask. Back-end developers often work with data and databases, so you will also benefit from learning some SQL. To help handle requests from databases, back-end developers can use Object Relational Mapping Tools, or ORM, to connect to the databases and retrieve the correct data. Although an ORM can hide some of the complexity of querying databases, it's useful to understand the fundamentals of databases so that you can troubleshoot any issues that arise. The day-to-day tasks of a back-end developer focus on the behind-the-scenes functionality that keeps websites, cloud apps, and mobile apps up and running. Back-end development covers a wide range of technologies, from managing user accounts, authentication, and authorization, to ensuring that sensitive data is stored and transferred securely. Back-end developers also work with databases, retrieving, processing, and storing data as required. Life for a back-end developer is varied, challenging, and ever-changing. Welcome to Teamwork and Squads. After watching this video, you will be able to define teamwork and describe the advantages of collaboration in software engineering, and describe squads. By definition, a team is a group of people working together towards a common aim. Within a team, you'll find a range of different people with different skills, experience, and talents. Each person can give their attention and effort to the things that they are good at, and by working alongside others on tasks outside their current repertoire, they can expand their skill set. Working in a team promotes creativity. Collaborating with others gives you the opportunity to discuss ideas and challenge one another's thinking about a subject. Good teamwork is empowering. Positive attitudes and behaviors can impact the rest of the team and create positive results. Working well as a team doesn't always come naturally, but there are some things you can consider to help your team succeed. Each member needs to trust and respect the other members of the team. This generally comes with time, but depends on all of the members contributing equitably. Defining and agreeing on goals for a project is essential so that the whole team knows what they are working towards. And you also need to define and agree on roles to avoid any duplication of effort or missed tasks. Working with each member's strengths is important to make the most of the talent within your team, as is celebrating success and analyzing problems. Communication is vital in a team environment. Ensure that you choose a method that works for everyone so you know that the whole team is seeing and responding to information. So, what does teamwork look like in software engineering? Teams often start projects with a kickoff meeting where they plan how they will complete the project, assign tasks, and agree on goals. Throughout the lifetime of a project, you're likely to have a whole team and/or sub-team meetings to review progress and plans. Design and code reviews can be requested at the team level and undertaken by whoever has availability at that point in time. Also, team members might present walkthroughs of their sections of responsibility to the rest of the team so that the whole team has oversight of all parts of the project. And key team members will likely present walkthroughs to stakeholders at various times during the project. When a project is complete, retrospective meetings may be held to review what went well and what could be improved in future projects. You may have a mentor who may or may not be in your current project team. You might also be asked to be a mentor. Sometimes team mentoring is used so everyone can learn from each other. And some groups also have teams working on internal projects, such as defining code standards, maintaining or updating legacy cross-project code, or reviewing potential new software for usefulness to the team. Good teamwork can bring many benefits to a project. Working alongside others can encourage creativity and enable you to take advantage of each person's strengths, while also allowing them to gain knowledge and skills from other members of the team. When working as part of a team, software engineers are more likely to adhere to corporate coding standards and regularly document their code. The additional accountability that teamwork creates results in better quality code, fewer bugs, and more maintainable code. From a software engineer's point of view, working as a team can reduce stress because there's always someone to turn to and get help from. And having someone to discuss problems with can help you to increase your understanding and resolve more issues by yourself. By working in a team, each member has a greater idea of the bigger picture, resulting in a more coherent overall solution. Some organizations that follow agile development methodologies may call a team a squad. Typically, a squad is a small team of up to 10 developers. It is likely to consist of a squad leader, who acts as the anchor developer and coach for the squad, and a few software engineers who develop and implement the product features and test cases. It may also include 1 or 2 user experience developers or designers. In some squads, the developers may work together in pairs to practice pair programming. You'll learn more about pair programming in another video. In this video, you learned that software engineering teams meet regularly throughout the duration of a project. Good teamwork encourages creativity, shares knowledge, and results in better quality code. And squads are small teams used in agile development. Welcome to Insider's Viewpoints, Teamwork in Software Engineering. In this video, we will hear from experts discussing how teamwork is important in software development and how teams work together.
Yeah, so teamwork is very, very important in the world of software development. As a software engineer, you're not just going to be sitting at your desk coding all day. One of the most important aspects of working on a team or on an engineering team is communication and knowing how to collaborate and speak with your team members about the code you've written, especially if you're going to a UX designer and say, hey, here's what I can do, and your spec is a bit off. Can we massage your specs a bit just so we can meet the coding requirements?
Incredibly important. While I think it's possible for a single person to engineer and deploy and run software, I think doing it as a team is both more impactful and gives you more potential to do bigger and greater things. I think it's also just a more fulfilling process when you're building something with a group of individuals. I think without the support structure, it's hard to build something and support it and maintain it just by yourself.
So teamwork to me is essential because we're talking to each other all day, and we're not only talking to our tech leads or senior engineer, we're talking to product managers, we're talking to UX designers, we're talking to business analysts, we're talking to data analysts, and so on and so forth.
You have the support system, you have diversity of opinions and perspectives in terms of how you go about building it. It's more satisfying. You kind of can take larger risks because you're in it together and you're there to support each other. I think the celebration of a job well done is a lot more, it's a lot more fulfilling when you're doing that with someone else. But I think it just gives you both kind of a larger range of scope and a larger sort of risk portfolio, if you will, and you're able to, I think, just get a lot more done, have a lot more checks and balances, and really gives you, there's a less likely chance that you're going to miss something or you're going to make a mistake. There's a lot of support there.
And so every project I've worked on has had at least 3 other people that I have needed to communicate with and to support, to be a reliable resource for them, to go to them for questions. Like I always have to be talking to somebody about something. So teamwork is crucial. Like you can't work in an isolated silo forever. At some point, you have to talk to someone else.
Building a product takes a lot of people. A lot of us come together to make a whole and to get the product shipped to production so our users can use it. And so teamwork is imperative.
Welcome to Pair Programming. After watching this video, you will be able to describe pair programming and compare different styles, and list the benefits and challenges of pair programming. Pair programming is an extension of teamwork where 2 developers work side by side at one computer. They can either be physically at the same computer or work virtually via video link or shared screens. The former is the preferred option, but virtual pair programming can also be productive. Pair programming is a type of agile development where 2 developers can plan and discuss their ideas continually as they create a solution, generally resulting in a better end product. And there are various styles of pair programming. Driver-navigator style is the most common style, where one developer is the driver typing in the code, and the other is the navigator reviewing the code as it's written and giving directions where to go next. The navigator also keeps an eye on the bigger picture of the overall solution. When working in this way, it's important to regularly swap roles to keep both of the pair engaged across the whole task. Ping-pong style incorporates test-driven development. For each task, one developer writes a failing test, and then the second developer writes code to pass that test. For each new task, they swap roles, so regularly changing who writes the test and who writes the implementation. The 2 developers work together at the end of each task, refactoring the successful code to refine and improve it. Strong style pair programming is a good way for junior software engineers to learn from more experienced ones. The defining rule for this is that for an idea to go from your head to the computer, it must go through someone else's hands. So the more experienced of the pair is the navigator, and the driver learns from witnessing their implementation and thought processes. For this to work well, the driver shouldn't challenge any ideas until the full implementation is complete, so as not to interrupt the flow of ideas from the navigator. Now, pair programming has many benefits. It's a good way to share knowledge and skills from one developer to another, or between the two, and a great way for a new team member to get up to speed on a project. As well as enhancing the technical skill of the pair, it's also a good way of building soft skills, such as communication and problem solving. Having two sets of eyes on the code often results in fewer typos, logic errors, and bugs. And it enables code reviews to be done on the fly. While this doesn't replace formal code reviews, it does enable another layer of review. Now, having two people thinking about a problem can result in multiple initial ideas, but is likely to result in the optimal approach being chosen earlier in the process. And although pair programming can take longer than individuals writing the same solutions, it's likely to result in better code with less time spent reviewing, testing, and bug fixing. There are also a few challenges to overcome. Working in a pair requires long periods of focus, which can be exhausting for the two programmers, and personal or other work commitments can impact the pair schedule. Sometimes one of the pair can end up controlling the entire process, resulting in a more typist programmer pairing, which doesn't benefit from any of the positives of pair programming. At other times, individual personalities may not work well together. When multiple sets of pair programmers are present, their discussions can result in a noisy environment for the other workers in the room. In this video, you learned that pair programming is an agile development technique where two developers work alongside each other. There are multiple styles of pair programming. And pair programming builds technical and soft skills, results in better quality code and solutions, and increases overall efficiency. Welcome to Insider's Viewpoints, Pair Programming. In this video, software engineers will discuss their experiences with pair programming and share their thoughts about the benefits and potential challenges associated with this way of working. First, we will begin by asking about their experiences with pair programming and about the benefits they associate with it.
At every job I've ever had, there have come times where you pair up with someone else. You get someone else sitting next to you at a computer, or you're sitting next to them at their computer. You're looking at a problem together, you're thinking about it.
Yes, I have actually. Some of the benefits are definitely working with an engineer who might be more of a senior engineer because they have a lot of insight and they obviously have a lot of experience doing what you're probably trying to figure out how to do. And it's really great when it's someone who can both guide you, but also kind of take a step back and not take over at the same time.
I think pair programming can be very beneficial. I think when you're working with someone together, it's an opportunity to learn. I think pair programming can be very great in circumstances where someone is new to a team, new to a programming language, new to a set of tools, or a development environment that is new to them. Sitting next to someone who's an expert, I think, can both help you ramp up more quickly. It can help the team itself sort of understand where you are in terms of your own knowledge and journey, and help put you in a place to both succeed and utilize you and your skills as best as possible. It does help you get real-time feedback. You don't necessarily have to wait for code to be sent out to be reviewed, and you can kind of brainstorm together in real time on the actual implementation of it.
Ultimately, I try to keep in mind that the goal of pair programming is that everyone has inherent blind spots in the way that they think and the way that they approach a problem. And if you are talking to somebody else, they can point out what your blind spots are. And they're going to have different blind spots than you as well. So you can point out their blind spots.
What do you think are the drawbacks and challenges of pair programming?
I think that can be a con sometimes when you're working with another engineer and you're trying to pair program is someone who kind of like takes over and then doesn't allow you to do your part or to learn, especially if they kind of like already know how to do something. So it's kind of like a double-edged sword. On the one hand, you want to get that practical experience of pair programming and you want to get that experience from someone else. But at the same time, you want to make sure that you're learning.
I personally find pair programming to be a little frustrating because the ways I go about solving problems can be very different than the ways other people go about solving problems. And it's not that I have some special, unique, wonderful technique. It's just that everyone's brain works differently. And watching someone else go through their workflow of how to solve a problem, they're not clicking the exact same buttons that you are. And that can get very frustrating to me. And it's like, why are you using your mouse to click all of those things? There's keystrokes for it. Like, you could be doing this so much faster. And so I find it a challenge to do pair programming sometimes.
You actually need calendar time, so you need to be able to dedicate time to sit together and work together and have an aligned schedule. You can either be physical, you can do it virtually, but you need to make the time to do it. Pair programming can come with some overhead in terms of getting off the ground. So if you have a tight time crunch, competing priorities, maybe just not enough, there might be not enough time in the schedule to allow for it. That can be one of the cons. That it can, while you can get long-term, I think, efficiency benefits from writing the code together, because then support in the future will be easier because you have more people who know how the code was written and what the intent was. So there are definitely long-term benefits, but there could be some short-term costs to it. So there are trade-offs in that sense.
Welcome to Introducing Application Development Tools. Getting your cloud app from the ideas stage to fully formed, written, and deployed is a long process, but there are many tools which will help you along the way. A cloud application developer's workbench includes version control, libraries, and frameworks. When many developers are working on the same project, knowing what order changes were made, thereby creating a new version of the source code, becomes overridingly important. Version control systems keep track of what changes were made when and by whom, and resolve any conflicts between changes. For developing your code, version control can be useful even when you are the sole contributor on a project. Properly used, it can give you a way to revert to an older version of your code if something goes wrong, and gives you some basic information about how the code developed over time. Version control functionality is generally tied to the storage system you are using, which is why a code repository is recommended, even for beginners. Git and GitHub are extremely popular for source code storage and management. Git stores files in repositories where you can track changes, split code into different branches for more focused development, and then merge them back into the main body of code. Libraries are collections of code, like standard programs and subroutines that you can use within your code. For example, you might want to include a navigational feature, like a carousel. A code library can supply you with the code for that so that you don't have to spend the time and energy creating one from scratch. Being able to reuse code in this way makes developing your app much quicker and easier. Multiple code libraries can be integrated into your existing project. As you discover a need for a specific function or feature, you can research an appropriate library. You determine when to call the required method as needed. The control returns to the program flow once the subroutine is finished. When you use a code library, you are in control. Code libraries are generally used to solve a specific problem or add a specific feature set. Either way, there are lots for you to choose from, so do your research. Here are some examples of code libraries. jQuery is a JavaScript library that simplifies DOM manipulation. Email Validator is a small library that checks an email address is correctly constructed and valid. Apache Commons Proper is a repository of reusable Java components. Frameworks provide a standard way to build and deploy applications. You can think of a framework as being a skeleton that you can extend by adding your own code, providing a scaffold on which to build your apps. The framework you intend to use must be determined early in your development planning and used right from the beginning. New frameworks can't be incorporated into an existing project. Your chosen framework dictates the architecture of your program and controls the program flow. The framework determines which subroutines and methods will be called when. When working with a framework, there is a specific structure that you must follow. The framework calls on your code rather than you calling on the framework. Frameworks are less flexible than libraries, allowing you less control, but they do provide good standardization and can help you create efficient code. To use an analogy, if you are a carpenter building a house, the framework is the frame that you add to, bricks on the outside, plasterboard on the inside, and so on. The frame acts as a guide for how the house is constructed. Here are some examples of frameworks. AngularJS is a JavaScript-based framework for dynamic web applications. Vue.js is a JavaScript framework focused on the user interface. Django is a framework that uses Python for web development. Frameworks define the workflow that you must follow, unlike libraries which allow you to call functions as and when required. When using a framework, it can sometimes feel like you, as a developer, are not in full control of the development process. This sense of the framework and its predefined workflow controlling the development process is referred to as inversion of control. Frameworks that have a lot of control are known as opinionated. They have opinions on how their workflow should be used and remove a lot of the decisions you would otherwise have to make about how code is written, the location of files, and even file names. Frameworks often include their own libraries, which they can call when needed. Inversion of control allows you to create standardized apps and takes away a lot of the tedious configuration work, so you can focus on the code for your app. In this video, you've learned about some of the tools that you will utilize in your career as a developer, including version control, libraries, and frameworks. Welcome to more application development tools. Let's look at some tools which can help you get your app built and deployed. CI/CD, build tools, packages, and package managers. CI/CD refers to the practices of continuous integration and either continuous delivery or continuous deployment. CI/CD is a best practice for DevOps teams, enabling developers to deliver frequent changes reliably. Implemented through a build automation server, continuous integration, or CI, ensures that all the code components work together smoothly. A CI build environment enables you to integrate newly developed code frequently, at least every day, if not every hour, depending on how quickly the project changes. Continuous delivery, or CD, begins where CI ends. The CI process automatically builds and tests your code, then CD deploys all code changes in a build to a testing or staging environment. A build tool transforms your source code into the binaries needed for installation. Build tools organize your source code, set compile flags, and manage dependencies. They are most important in environments where there are many interconnected projects with multiple developers contributing to each project. In these environments, it can be very difficult to keep track of what changes were made, in what order, what dependencies exist, and what needs to be incorporated in the next build. So automation is key to keeping everything running smoothly. Build automation can automate a wide variety of tasks that developers do in their day-to-day activities, like downloading dependencies, compiling source code into binary code, packaging that binary code, running tests, and deployment to production systems. You can initiate a build from the command line or from an IDE. There are two categories of build tools widely in use. Build automation utilities, which generate build artifacts like executables by compiling and linking source code. Build automation servers, which execute build automation utilities on a scheduled or triggered basis. Some examples of build tools are Webpack, a model bundler for JavaScript, and Babel, a JavaScript compiler. Now that you have your app developed and tested, you're ready to deploy. But how does that happen? The app needs to be simple and trouble-free for the user to install. So a commonly used technique is to collect all the necessary files and bundle them together into a package. Packages are archive files that contain the app files, instructions for installation, and any metadata that you choose. They have their own metadata too, including the package description, package version, and any dependencies, like other packages that need to be installed beforehand. Once you have bundled your app into a package, you can use a package manager to distribute it. Package managers take care of the tasks of finding, installing, maintaining, or uninstalling software packages at the user's request. Package management systems coordinate with file archivers to extract package archives. Verify checksums and digital certificates to ensure the integrity and authenticity of the package. Locate, download, install, or update existing software from a software repository. And manage dependencies to ensure a package is installed with all packages it requires. Some commonly used package managers for each of the major platforms are listed here. On Linux, Debian Package Management System, or DPKG, Red Hat Package Manager, or RPM. On Windows, Chocolatey. On Android, Package Manager. On Mac OS, Homebrew and MacPorts. Any libraries or utility code that is developed as part of the application is managed with the Cloud Application Package Managers. Here are some examples of package managers for popular languages. For Node.js or JavaScript, NPM. For Java, Gradle and Maven. For Ruby, RubyGems. For Python, pip and conda. In this video, you've learned about some of the tools that you will utilize in your career as a developer, including CI/CD, build tools, packages, and package managers. Welcome to Introduction to Software Stacks. After watching this video, you will be able to describe software stack terminology, identify some commonly used software stacks, and list the benefits and challenges of different software stacks. A software stack is a combination of technologies that include software and programming languages. Developers use a software stack to create applications and solutions such as web and mobile apps. The set of individual technologies is stacked in a hierarchy and work together to support the execution of an application. The higher levels in the stack provide tasks or services for the user, and the lower levels interact with the computer hardware. Software stacks typically include front-end technologies such as programming languages, frameworks, and user interface tools, and back-end technologies such as programming languages, frameworks, web servers, app servers, operating systems, messaging applications, and databases. You might hear the term technology stack used in place of software stack. However, a technology stack is a broader term that includes hardware and infrastructure, like virtual machines, containers, storage, and load balancers, as well as the software stack. The simplest implementation of a software stack consists of a presentation layer, a business logic layer, and a data layer. However, more complex applications use more complex stacks, which could include software for virtualization, scheduling and orchestration, runtime environments, database connectivity, networking, and security. The software and services that make up a stack can be from a variety of sources, from internal resources to third-party providers to cloud providers. There is no formal definition of the structure of a stack, the only rule being that the software and the services included must support an application's development, functionality, or deployment. When you're using a software stack, you don't have to use all of the available layers, you only need to use those which are relevant to your solution. There are many different examples of software stacks. The Python Django stack uses the popular Python programming language alongside the Django web framework. This combination is all open source and commonly used for large-scale, fast-changing web applications. The Ruby on Rails stack uses the Ruby programming language with a server-side web application framework. Ruby on Rails is great with JSON or XML for data transfer, and HTML, CSS, and JavaScript for front-end development. And the ASP.NET Stack includes Microsoft technologies such as the ASP.NET MVC framework, the IIS Web Server, SQL Server, and Azure. You'll learn more about the LAMP, mean, MEVN, and MERN stacks next. The LAMP stack runs on the Linux operating system. It uses the Apache HTTP or web server, MySQL databases, and the PHP programming language. LAMP is an example of an early incarnation of a software stack designed for building websites and cloud applications. All its constituent parts are open source and loosely coupled, so it's easy to swap different options into the stack. For example, you could choose to use PostgreSQL instead of MySQL for your database server, changing the LAMP stack to be the LAPP stack. Similarly, you could use the Python programming language instead of PHP. The mean stack uses a MongoDB database with an Express.js web application server framework, the AngularJS framework for front-end JavaScript development, and the Node.js platform for server-side scripting. The mean software and services are platform agnostic, free, and open source. And there are other stacks related to the mean stack, including the MERN stack, which replaces AngularJS with React and is a flexible and high-performing framework for developing front ends, and the MEVN stack, which replaces AngularJS with Vue.js. Vue is a lighter-weight JavaScript framework with less capabilities, but it can provide better performance than AngularJS. Let's consider some advantages and disadvantages of three different software stacks: Mean, MEVN, and LAMP. Mean is a free and open-source JavaScript software stack used for building web applications. The biggest advantage of the mean stack is that all of the parts use JavaScript, so developers only need to know a single language. The stack is also open source, which means the cost is lucrative to businesses, and there is a lot of documentation and reusable code for developers to use. Development can happen quickly because Node.js has a huge collection of free, reusable module libraries. However, the mean stack may not be well suited for large-scale applications. When using Express.js, the business logic often resides on the server, preventing the reuse of some services, like batching operations. And MongoDB is great for unstructured data, but it doesn't provide the same level of functionality as a relational database. The MEVN stack is a web stack, like Mean, but it uses Vue.js instead of AngularJS for user interfaces. MEVN and Mean stacks have similar advantages, but Vue.js is a much newer technology and doesn't have as many reusable libraries as AngularJS. Like Mean and MEVN, the software and services in the LAMP stack are open source, meaning that there are lots of reusable chunks of code available to the developers. And because LAMP is one of the oldest software stacks, it's easy to find support and reusable solutions. However, because the Linux operating system is an integral part of the stack, it isn't as flexible as Mean and MEVN, which are platform agnostic. MySQL is a relational database, so the stack cannot take advantage of unstructured data. The other disadvantage of the LAMP stack is that the back end runs on PHP, Perl, or Python, whereas the front end uses JavaScript and HTML, making it harder for developers to switch back and forth between the Mean and MEVN stacks, which use JavaScript throughout. In this video, you learned that software stacks are a combination of technologies for creating applications and solutions. Software stacks can range from simple 3-layered systems to many layers. There are numerous types of software stacks for different developers and environments. The Mean, MERN, and MEVN stacks use JavaScript throughout and are suited to large-scaled apps using relational data. And the LAMP stack on Linux works well for non-relational data. Welcome to Insider's Viewpoints, Tools and Technologies. In this video, we will hear from experts discussing their favorite tools and technologies for software engineering projects.
Our team uses Git and GitHub every single day for all of our projects. We use it for tracking code, we use it for collaboration, and we use it for tracking bugs, features, and tasks for all of our projects.
I believe most open source projects are now using Git. Every project I've contributed to, whether open source or closed, has used it. Git's true value is most apparent when you're working on a team with multiple people, at which point you'll be glad to have things like feature branches and pull requests. But even if you're working on a project where you're the sole committer, I recommend using Git, and in particular GitHub, for the community aspect.
So if you are a front-end developer, if you understand JavaScript, then picking up backend using a framework like Node.js is not that much of a stretch. I actually started building static websites, and then slowly learned how to put in dynamic content using JavaScript, and then I had to use Java or PHP to build my backend systems on the server.
For front-end development, you're primarily using HTML, CSS, and JavaScript. If you're very front-end focused, you might want to try out an IDE built for that specific purpose, such as brackets. If you want to keep things more general, I recommend VS Code. In either case, I recommend installing IDE extensions for automatic formatting and linting of your code using Prettier and ESLint. These will help you catch issues as early as possible. For backend development, the tools are quite a bit more varied, so it's hard to give specific recommendations, but if you choose Node.js, you'll be able to use some of the same tools that I mentioned for front-end development. Otherwise, I recommend just looking into what IDE extensions are available and what linters and auto formatters are available.
JavaScript is a very powerful language. It lets you do pretty much anything you can imagine, including shooting yourself in the foot if you're not careful. The practices I typically follow with JavaScript include proper scoping of variables and functions, and writing unit and integration tests for my features.
React.js was developed at Facebook, very popular. Angular is a framework operated by Google that allows for development of single-page applications, SPAs. jQuery is possibly the most popular and oldest library out there, created by John Resig in 2006. And jQuery is frequently used with both Angular and React. Backbone is a lightweight JavaScript library that is very popular. In terms of backend languages and frameworks, Node.js is an open source server-side platform built on the Google Chrome JavaScript engine. It uses an asynchronous single-threaded architecture that allows it to serve a very large number of concurrent connections. Flask is a framework used on Python that is popular with Pythonistas. And the Spring framework based on Java has been around for years and remains popular.
We use React JavaScript framework. It is better than Angular in terms of speed and efficiency. React is easier to learn than other JavaScript frameworks, which makes its adoption in the team easy. It also resolves the problems related to cross-browser issues. Another great feature of React is the use of JSX. JSX is helpful when working with UI inside the JavaScript code. It helps React to show more useful error and warning messages.
My favorite front-end JavaScript framework would be React.js. I love the whole component-driven design and architecture that you have to follow when you create a React.js based application. I also like the idea of props and states to hold the state of your application.
By using Express.js for backend development, we are able to scale applications quickly. We can code both frontend and backend with the help of JavaScript easily by using Express.js. Express.js is supported with the Google V8 engine, with the help of which you would be able to get higher performance without any lag or error in processing. It also supports the caching features, so you would not have to re-execute the codes again and again. Moreover, it will help web pages to load faster than ever.
When working with Node.js, I'll give you two of my favorite packages that I use on a daily basis. So first is making requests to web services. I use a library like Axios that helps me create these requests with the right headers and also provide me with callback functions or promises to be able to handle the responses that come back. My second package would be when I'm working with databases. I'll use NPM packages more likely than not to talk to an external database, regardless of if it's a relational database or a NoSQL database.
So when writing JavaScript, I really like to take advantage of the features in ES6 because it can make my code look cleaner, easier to read, and just more beautiful, such as the arrow functions or the ... operator. And so I encourage you to, after learning JavaScript, dive into ES6 a bit and have fun with it.
Welcome to Interpreted and Compiled Programming Languages. After watching this video, you will be able to identify interpreted programming languages and identify compiled programming languages. What are programming languages? Programming languages help us tell computers what to do. Computers don't use human language, they use their own language called machine code. Machines understand binary code, that is, ones and zeros, so to make communicating with computers easier, we have human-readable programming languages. Two common categories for programming languages are interpreted and compiled. These are broad categories, and there are many programming languages that are classified under compiled languages and interpreted languages. The purpose of the project helps a developer determine which programming language is best. Interpreted language is also commonly referred to as scripted or scripting language. Programs written in interpreted or scripted language, like Python and HTML, run through the programming interpreter on your computer's operating system or in your web browser. Remember that programming languages are in human-readable code, so the interpreter takes the human-readable scripted code and then translates it into machine code, enabling the computer to complete the requested task. As computers and web pages have changed and advanced, some interpreted programming languages are outdated, and they are not as useful or relevant. Some other languages are more versatile and easier to learn, which means they are preferred over other scripting languages and are used more often. All interpreted programming languages need an interpreter to translate the source code. Translators are built into your web browser, or they require a program on your computer to translate the code. Several different interpreted programming languages exist. Some examples of common interpreted programming language types are JavaScript, a simpler scripting language that runs through the web browser interpreter; Python, a language that is popular because it is easy to learn and use for developers; Lua, a general-purpose, lightweight game scripting language that is easy to learn and use; and HTML, a markup language used for formatting web pages. Another category of programming languages is the compiled programming languages. Compiled programs are applications and programs, like your music app or your operating system, that you run on your computer or device. The programs are packaged or compiled into one executable file. They are usually larger programs. Compiled programs are used to help solve more challenging problems like interpreting source code. Compiled programming languages are often referred to more simply as programming languages. A compiler program creates a program file, which runs the software. Simply put, it piles the code into one file that runs when you double-click on the app on your device. The program runs faster, and it can be done repeatedly. The source code is converted from the programming language to machine code. Then it is compiled into one executable file. Finally, the program runs when you select the icon or file on your device. Some examples of compiled programming languages are C and its variations, C++, and C#, which are used in many operating systems like Microsoft Windows, Apple's Mac OS, and the open source operating system, Linux. Java is another compiled programming language. It shouldn't be confused with the interpreted language JavaScript. The Android OS is written in Java because it works well across computing platforms. Let's look at this process. When you update to a new version of your operating system, like Microsoft Windows, your device might download an installation program. That program is made up of many files. The files are written in a compiled programming language. These files give instructions to your device in machine code. The compiled program is running on your device. A compiled program that you commonly use is your device's operating system, such as Linux, Microsoft Windows, Apple's Mac OS, or Android. Your operating system is written in a compiled programming language, like C, C++, C#, or Java. In this video, you learned that interpreted programming languages run scripts that are repetitive and need to be run often. Interpreted programming languages are more versatile and can be used across platforms as long as there is the correct interpreter. Some examples of interpreted programming languages are JavaScript, Python, and HTML. Compiled programming languages are for more complex programs that complete larger tasks. Compiled programming languages are used for creating executable files that can run directly from your device. And some examples of compiled programming languages are C and Java. Welcome to Comparing Compiled and Interpreted Programming Languages. After watching this video, you will be able to compare interpreted and compiled programming languages and discuss interpreted and compiled programming languages. How do developers choose a programming language? Developers choose which programming language is best to use depending on what they have the most experience with and what they trust, what is best for their users, and what is the most efficient to use. What are interpreted and compiled programming languages? Interpreted programming languages are used to create a scripted source code for smaller tasks. The source code goes through an interpreter. The interpreter is built into the operating system on a computer or on a web browser. Compiled programming languages are used to create files. The files are executable files. They are then grouped in programs that you can run on a computer or device. Interpreted programming languages are also called script code or scripting because they are used to automate tasks. Interpreter programs read and execute the source code line by line like someone would read a script. Each time the program runs, the source code needs to be executed to receive the desired output. And source code written in one of the interpreted programming languages runs on almost any operating system with the right interpreter. For example, imagine you have a client requesting information about web page views for last month. Which type of programming language would be the most appropriate and efficient to create a program for this task? You would use one of the interpreted programming languages to write code for a script. The script would retrieve the web page views data and then put it into a table for the client to read. Compiled programming languages are also called programming languages for short. They are used for more complex programs that complete larger tasks like running a spreadsheet program on your computer. A compiled programming language is used to write a larger program, usually installed on your device as an executable file. Writing code in a compiled language does take longer, but the payoff is that the program's code runs faster because compiled programs are installed on the device. And once the program is coded, the compiled program is grouped into one downloadable file. Remember that client who wanted information about web page views? Now they want a spreadsheet program to view and manage the data. A programmer could use the C programming language to create a compiled program like Microsoft Excel. So, what are the major differences between interpreted programming languages and compiled programming languages? First, there's interpreted programming. These programs are available across multiple platforms or in the cloud. The scripting languages are easier to learn and use, and they're better for websites because they tackle smaller, repeated processes. Then there's compiled programming. These programs are available to users with the same operating system coded in the same language. However, compiled programming languages are more difficult to learn and use because they are larger programs with more parts. And they're better for larger tasks like running the operating system on your computer. To better understand more of the similarities and differences of programming languages, let's take a look at some examples. A few of the most common programming languages are C, C++, and C#. C is a compiled programming language. C is the original language, and C++ and C# are variations. C and its variations are case-sensitive languages. The C programming language is the basis for Windows and other common operating systems, and it takes more time to learn and use for coding, but requires less memory and the code runs faster. Another common programming language is Java. It is a compiled programming language. It is also a case-sensitive, object-oriented programming language. The Java Virtual Machine, or JVM, is required to run the code written in Java. It is the primary programming language for some operating systems, like the Android OS. And a benefit of Java is that it is a cross-platform language, which means it runs the same code on Mac OS, Windows, and Linux. Python is an example of an interpreted programming language. It is also referred to as a scripting language. Python is a popular general-use case-sensitive programming language. It is used with Windows, Mac OS, and Linux operating systems, and with server-side web app code. And it requires the Python engine to interpret code. JavaScript is another interpreted programming language. It is a scripting language that runs on the client side in web browsers. JavaScript is case-insensitive. Simple scripts are run with HTML. Complex scripts are run in separate files. And while it sounds similar, it shouldn't be confused with Java, the compiled programming language. Another example of a common programming language is HTML. It is an interpreted programming language. HTML stands for Hypertext Markup Language. HTML is mostly case-insensitive with some exceptions, and it uses tags to format web pages on client-side web browsers. In this video, you learned that Interpreted programming languages create source code that runs through an interpreter in your device's operating system or on your web browser. Compiled programming languages create executable files that are grouped in programs on your device. Compiled programming languages, like C and Java, are used to write larger programs like operating systems and other executable files. And interpreted programming languages, like Python and HTML, are used to write code that can complete repetitive tasks within a web browser or a computer. Welcome to Query and Assembly Programming Languages. After watching this video, you will be able to compare high-level and low-level programming languages, describe query languages, and describe assembly languages. Let's explore query and assembly programming languages. But first, we need to categorize programming languages into two levels, high-level and low-level. A high-level programming language is more sophisticated and uses the common English language to make its code more understandable and to increase the speed of coding and debugging programs. Examples of high-level programming languages include query languages, such as Structured Query Language or SQL, structured programming languages, such as Pascal, and object-oriented programming languages, such as Python. In contrast, a low-level programming language uses a set of symbols to represent machine code. Examples of low-level programming languages include assembly languages such as ARM, MIPS, and x86. A query is a request for information from a database. The database handles the query and searches its tables for the information requested and returns the results to the querying entity. When querying a database, it is important that both the user application making the query and the database handling the query are speaking the same language. In programming terms, writing a query means using predefined and understandable instructions to make the request to a database. This is achieved using programmatic code, and this is what we refer to as a query language. A query language may also be referred to as a database query language. By far the most prevalent query language for database queries and database management is SQL. However, there are other query languages available, such as AQL, CQL, Datalog, and DMX. In addition to SQL databases, there is another type of database called NoSQL, which stands for Not Only SQL. The key difference between these two types of databases is their data structures. While SQL databases are relational and use structured, predefined schemas, NoSQL databases are non-relational in nature and have dynamic schemas for unstructured data. A query language is predominantly used to request data from a database or to create, read, update, and delete data in a database. You will likely see the term CRUD used to refer to these last four key database operations. Typically, a user enters a command to either make a query or perform a CRUD operation using syntax that is understandable to the database management system hosting the database. And a database typically consists of structured tables made up of multiple rows and columns of data. When a user performs a query, the database retrieves the data from the relevant rows and columns in the table and arranges it into some sort of order ready to be returned and presented in the query results. Database queries are either a select command or an action command such as create, insert, update, or a mixture of both. The term statement is more commonly used to describe these commands. Select queries request data from a database, whereas action queries manipulate data in a database. Query statements can also be used to perform other administrative functions, such as creating users and modifying permissions. This table lists some of the most common SQL query statements. And here are some simple syntax examples of common SQL statements. As mentioned earlier, assembly languages are less sophisticated than query languages structured programming languages, and object-oriented programming languages. As an assembly language uses a simple set of symbols to represent the zeros and ones of machine code, it is categorized as a low-level programming language. Assembly languages are closely tied to the processor architecture from hardware manufacturers, and therefore each CPU type will typically have its own assembly language. For this reason, there are a large number of assembly languages in use today, which vary among hardware manufacturers. Assembly languages use a simple, readable format for their statements, and they are entered one line at a time with one statement per line. Assembly language statements use the standard format shown here. In this syntax, all fields in curly brackets are optional, and the statement has two main parts. The first part is the instruction, or the mnemonic, and the second part includes the parameters, or the operands. There may also be optional useful comments added on the end of the statement. One other key difference with assembly languages is that they are translated using an assembler instead of a compiler or interpreter, and one statement translates into just one machine code instruction, as opposed to high-level languages where one statement can be translated into multiple machine code instructions. Assemblers translate assembly language into machine code using mnemonics, such as input INP, output OUT, load LDA, store STA, and add ADD. The statements consist of opcodes that tell the processor what to do with the data, and operands that tell the processor where to find the data. In this video, you learned that query languages, structured programming languages, and object-oriented programming languages are categorized as high-level programming languages. Assembly languages are categorized as low-level programming languages. A query language is predominantly used to request data from a database or to manipulate data in a database. The most prevalent query language for database queries and database management is structured query language, or SQL. Select queries request data from a database, whereas action queries manipulate data in a database. You also learned that assembly languages use a simple set of symbols to represent the zeros and ones of machine code. Assembly languages are closely tied to the processor architecture from hardware manufacturers. Assembly languages are translated using an assembler instead of a compiler or interpreter. And assembly language instructions have a one-to-one association with their machine code counterpart. Welcome to Understanding Code Organization Methods. After watching this video, you will be able to explain why code organization methods are important when programming, define the different code organization methods, and identify the benefits of using code organization methods. Organizing is very important when it comes to reading, maintaining, and configuring code. Well-planned out software design, usually using one of several methods, helps programmers write cleaner and more reliable code. Planning out code in a visual format helps improve the code base once it is written and reduces the chance of bugs and errors throughout the lifespan of a project. Organizing code before programming has a positive impact on the quality of the program and helps provide a consistent and logical format to use while coding. There are two main methods of organizing code: flowcharts and pseudocode. The main difference between pseudocode and a flowchart is that the former is a basic high-level description of an algorithm. An algorithm is a step-by-step sequence of solving a given problem. A flowchart is a pictorial representation of an algorithm, showing the steps as boxes of various shapes and colors connected by arrows that indicate their order. Flowcharts are used in designing or documenting a process or program. Pseudocode provides a beneficial bridge to the project code because it closely follows the logic that the code will. Pseudocode also helps programmers share ideas without spending too much time creating code, and it provides a structure that is not dependent on any one programming language. Flowcharts are especially beneficial for smaller concepts and problems, while pseudocode is more efficient for larger programming projects. And flowcharts provide an easy method of communication about the logic and offer a good starting point for the project because they are easier to create than pseudocode in the beginning stages. A flowchart is the graphical or pictorial representation of an algorithm using different symbols, shapes, and arrows in different sizes and colors to demonstrate a process or a program. The main purpose of using a flowchart is to analyze different methods of solving a problem or completing a process. Several standard symbols are applied in a flowchart, and you can easily highlight certain elements and the relationships between each part in the process. Some traditional flowchart shapes used for programming concepts are start-end, a capsule, process, a rectangle, decision, a diamond, data, a parallelogram, and connectors as arrows. A simple flowchart to represent how to add two numbers is easy to create. The procedure starts with the capsule and has a connector or arrow progressing to the next step, the data input, the parallelogram, in this case, input N1 and input N2. Then another connector or arrow goes to the process, the rectangle of adding the two inputs, sum equals N1 plus N2. Another connector or arrow moves to the data, the parallelogram showing the result, in this case, print sum. And the last connector or arrow moves to the end of the process, the end capsule. Flowchart software is an application that provides various functionalities to create flowcharts by providing the ability to drag shapes into the desired order using an easy-to-use editor. Flowchart software also provides team collaboration for creating flowcharts. Some of the well-known flowchart software programs include Microsoft Visio, Lucidchart, Draw.io, and Draw Anywhere. Pseudocode is an informal type of programming description that does not require any strict programming language syntax or underlying technology considerations. System designers write pseudocode to ensure that programmers understand a software project's requirements and align code accordingly. Pseudocode is used for creating an outline or a rough draft of a program that summarizes a program's flow but excludes underlying details. Pseudocode acts as the bridge between the programmer's brain and the computer's code executor that provides the ability to plan instructions that follow a logical pattern without including all the technical details. Pseudocode is a great way of getting started with software programming as a beginner without worrying about coding syntax. Pseudocode helps both programmers and non-programmers agree about the program's goal and the basics of how the task should be done. Here's one example of pseudocode written to check if the user entered an odd or even number. The next example displays the pseudocode written in C++. There are many advantages of using pseudocode over flowcharts. The main benefit of pseudocode is that it's simple and explains exactly what each line of an application should do. The coder can focus more on logic than on program language syntax. Removing the distractions of coding when using pseudocode makes the code development stage easier. Words and phrases in pseudocode represent lines of basic computer operations that simplify translation from the pseudocode algorithm to the specific programming language. Pseudocode allows programmers working in different computer languages to interact with each other. Pseudocode can be reviewed by different development groups, easier than real code. Pseudocode is easier for non-programmers to read and enables quick and easy translation to any computer language. Writing pseudocode is more concise and easier to modify, so changes to the design can be easily incorporated. And lastly, unlike some flowcharts, pseudocode is usually less than 1 page. In this video, you learned that organizing and planning out software design enables programmers to write cleaner and more reliable code. And organized code is very important from a readability, maintainability, and scalability standpoint. Two main methods of organizing and planning software code are by developing flowcharts or writing pseudocode. A flowchart is a pictorial representation of an algorithm, showing the steps as boxes of various kinds, connected by arrows that indicate their order. And the main goal of pseudocode is to explain exactly what each line of a program should do, making the code construction phase easier for the programmer. Welcome to Insider's Viewpoints, Types of Languages. In this video, we will hear from experts discussing if they prefer developing in compiled or interpreted programming languages.
Most of the time, it doesn't really matter. It just comes down to personal preference, like what are you going to get moving on the fastest? There are certain situations where it will make a difference if you're compiling ahead of time versus interpreting on the fly. If you're trying to eke out like very small incremental performance benefit.
I prefer compiled code or a language that's compiled language, just because I have more of a guarantee that it will, well, maybe not necessarily work, but will do what I thought it will do, and at least will deploy properly when being rolled out.
But usually, no, it doesn't make that much of a difference to either the development process or the like deployment and use process. They definitely have advantages and disadvantages to each of them, but most of the time doesn't make that much of a difference to what I'm doing. I
think interpreted languages can, there's a lot of like flexibility there, and often you can do more creative things, and the compiler, it sort of stops, the buck stops with the compiler, and you can't really avoid compiler errors with the compiled language. With interpretive, there's more interesting runtime possibilities there. So I think it really depends on what environment you're developing for, or what your risk factor is when it comes to being okay with potentially buggy code being out in the wild.
What do you think are the benefits of object-oriented programming over procedural programming?
Anything can be an object, and object-oriented design puts hierarchies and patterns onto those things, and that structure can make it easy to keep designs in mind and keep in mind how the different objects interact with each other. It's also very easy in object-oriented programming to paint yourself into a wall where you have put too much structure around everything, and you now have this like explosion of useless boilerplate code. So there's a bit of a, not catch-22, but just a balance that you need to find in between how much structure should your thing have, how much flexibility should it have, and how much should your intentions be imposed on that design and the way that people interact.
I think procedural programming can be, feels more mathematical and more sort of like pure engineering in some sense, and I think that that also can lend itself well to someone who is really looking to not just build software, but really wants to sort of feel like they're engineering the code in some sense. It can feel like you're kind of like in the machine, if you will. So I know maybe that's a weird answer, but I think it depending on how your brain works too, one can lend itself more easily than the other. So, but I think it's worth trying them both out.
If you get super object oriented, you can get a little too prescriptive with the designs, I think. So that's just whenever you're using objects, it's just a thing to keep in mind that you can go too far with it. But where that line of too far is kind of depends on exactly what it is that you're building. Sometimes the sky's the limit, just regulate everything. And sometimes the amount of flexibility that you require actually does mean that you can't really have an object of any sort. Both of those situations should be pretty rare. Those would be on the extremes. But most of the time, a few simple objects will do a lot of good no matter what the rest of your system looks like.
Yeah, I think object-oriented programming to me is for me personally, I think it does lend itself well to like real-world mappings and data models, and the sort of classic examples of you might in your first object-oriented software like demo build something like a library that has books and it has a checkout. So like there's physical objects, and the way you learn it is very much sort of, you think about the software as something real world. So that helps you make the jump from building something physical with your hands to building something with bits and bytes.
Welcome to Branching and Looping Programming Logic. After watching this video, you will be able to describe the two types of programming logic, define Boolean expressions and variables, and list the differences between branching and looping. There are two major types of programming logic, branching and looping. Both types use Boolean expressions and variables. A Boolean expression is a type of programming statement with only two values, either true or false. And variables have assigned values that are passed into a function or subroutine within a more extensive program. Computers use Boolean logic to make decisions. The computer takes one action if a Boolean expression is true and a different action if the expression is false. Typically, a program consists of instructions that tell the computer what to do and data that the program uses when it is running. A variable has a value that can change depending on conditions or information passed to the program. Boolean logic, along with variables, form the basis of programming. Branching logic is where a computer makes a decision following a different set of instructions depending on whether certain conditions are met during the program's execution. Each possible code pathway creates another branch. The branch of code that runs depends on the values assigned to the parameters of the branching procedure, and there is no limit to the number of branches to implement complex logic. The values of these parameters may be input by the user or generated by the output from a previous procedure. Branching contains constructs that occur and are processed to determine the path a program takes when running. Branching statements, also known as constructs, allow the execution flow to jump to a different part of the program. The common branching statements used within other control structures include if then else, switch, and goto. The if statement is a decision-making construct that guides a program to make decisions based on specified criteria. The if statement executes one code set when a specific condition is met, true, or another code set if the condition is not met, false. The if-then-else is a conditional construct that executes its substatement, which follows the then keyword. This only occurs if the provided condition is true. The if-else statement extends the if statement by specifying an action if the if, or true-false expression, is false. With the if-else statement, the program will execute either the true code block or the false code block, so something is always performed with an if-else statement. In computer programming languages, a switch statement is a type of selection control mechanism used to allow the value of a variable or expression to change the control flow of program execution via search and map. Goto is a statement found in many computer programming languages that performs a one-way transfer of control to another line of code. In contrast, a function call typically returns control. Now, let's look at the logic of looping programming. A loop is a sequence of instructions that continually repeats until reaching a specific condition. Typically, a particular process is performed, such as retrieving and changing data, and then some conditions are checked, such as whether a counter has reached a prescribed number. If it has not, the next instruction in the sequence is to return to the first instruction in the series and repeat the sequence. If the condition is reached, the next instruction falls through to the next sequential instruction or branches outside the loop. A loop is a fundamental programming idea commonly used in writing programs. There are 3 basic loop statements: while, for, and do while. In a while loop, a condition is evaluated before processing the body of the loop. If a condition is true, then and only then the body of the loop is executed. In a for loop, the initial value is performed only once. Then the condition tests and compares the counter to a fixed value after each iteration, stopping the for loop when false is returned. And in a do-while loop, the condition is always executed after the body of a loop. It is also called an exit-controlled loop. In this video, you learned that there are 2 major types of programming logic, branching and looping. Both types of logic use Boolean expressions and variables. Boolean expressions have only 2 possible values, either true or false, and variables have assigned values that are passed onto a function or subroutine within a more extensive program. Variables have values that can change depending on conditions or information passed to the program. And branching is deciding what actions to take, while looping is deciding how many times to perform a certain action. Welcome to Introduction to Programming Concepts Part 1. After watching this video, you will be able to describe the purpose and use of identifiers in programming, and describe the purpose and use of containers in programming. To fully understand software programming, there are some fundamental programming concepts you need to know first. The first concepts you will look at are identifiers. Software developers use an identifier to reference a program component, such as a stored value, a method, an interface, or a class, by assigning a custom named label to it. If the identifier stores data, then the data values in the program can be one of 2 types, either a constant or a variable. A constant is a data item whose value does not change within a program. This could be a numerical constant, such as the mathematical value of pi, or it could be a text string that remains constant, such as a player's name within a game. Constants are also referred to as named constants. You assign a value to a constant when you define it. For example, you might want it to refer to a numerical value within your program, such as pi, or a cost price, or a rate of tax. And then, rather than repeatedly retyping the same numerical value, you can just declare a constant for the value instead and name it something meaningful like pi_value or cost_price or tax_rate. There are a couple of major benefits to using constants in your programs. One is for ease of readability in your code, and the other is that if the specified value changes in the future, you only need to change it once on the constant, rather than finding every instance of that numerical value within your code and changing it. The other type of identifier used in programming is a variable. As the name suggests, this kind of identifier is not constant. Its value can change during the program's execution, such as a user entering their age in an application or a high score in a game. Variables can be strings of text, numerical values, or any other type of data. Using a variable as an identifier is a useful way to refer to program items that are unknown to you, such as a username, a service, or a file name, for instance. If you don't use a variable, then you will need to hard code all the names and values in your program, which is not considered best practice. Variables can be declared and assigned a data type and initial value as they are defined, or you can decide not to assign an initial value when you define a variable and instead have the value assigned later by instructions within the program. In addition to the identifier data structures already discussed, there are also special kinds of identifiers that can reference multiple elements in a program, and these are referred to as containers. Being able to specify multiple elements means that you don't have to create a variable for every individual element. This makes it faster and more efficient. For example, If you only want to store 6 numerical integers, then you could argue that you could just create 6 variables, one for each. But what if you need to store 1,000 integers or more? In such a case, defining 1,000 variables would obviously be an unwieldy and inefficient programming technique. So in this case, you would use a container. There are 2 types of containers to specify multiple elements: arrays and vectors. The simplest of these container types is an array. In an array, a fixed number of elements of the same type are stored in sequential order starting from index 0. When you declare an array, you specify the data type of the values it contains, such as an integer, or Boolean, or a string, and then the maximum number of elements it can contain. The syntax for declaring an array is to specify the data type first, then the name of the array, then the maximum size of the array in square braces. In contrast to arrays that have a fixed size, vectors have a dynamic size, and they will automatically resize themselves as you add elements to them or remove elements from them. For this reason, you may also see them referred to as dynamic arrays. Because they are dynamic in nature, vectors take up more memory space than arrays, and their elements also take a little longer to access than elements in an array, as they are not stored in sequential memory locations. The syntax for declaring a vector is to specify the container type of the vector first, then specify the data type in angle brackets, then the name of the array. Note that because it is a vector, you do not need to specify a maximum number of values it can contain because the size is not fixed, it is dynamic. In this video, you learned that software developers use an identifier to reference a program component. If an identifier stores data, then it can either be a constant or a variable. A constant is a data item whose value does not change within the program. A variable is not constant, it can change during the program's execution. In an array, a fixed number of elements of the same type are stored in sequential order, starting from 0. And vectors have a dynamic size, and they automatically resize themselves as elements are added or removed. Welcome to Introduction to Programming Concepts, Part 2. After watching this video, you will be able to describe the purpose and use of functions in programming, and describe the purpose and use of objects in programming. Next, let's look at the fundamental concept of functions. Functions are a consequence of the modular programming software development methodology that encourages the separation of a program into multiple modular components where each performs a specific task within a program. So, a function is essentially a piece of structured, standalone, and reusable code that will perform a single specific action. This enables software developers to take a substantial, complex program and divide it into smaller, more manageable, and focused pieces. Although some programming languages may refer to them as something else, such as subroutines, procedures, methods, or modules, most modern programming languages refer to them as functions. Functions take in data as an input, then process the data, and then return the result as an output. There are essentially 2 types of functions. Standard library functions are the built-in functions provided by the programming language. Common examples include the if, else, while, and print functions. But programming languages also allow you to write your own functions. And once you've written a function, you can use it over and over again. The way that the blocks of code that make up a function are identified is different across programming languages. Some use braces, some use begin and end statements, and others use indentations, for example. There are a few steps to using functions. The first thing you need to do is define or create a function. When you define a function, you provide a function keyword, then give the function a unique name, and you provide the statements that make up the body of the function. Once a function has been defined, it then needs to be called or invoked. When you call a function, the specified actions within the function are performed using any specified parameters. While defining and calling functions are common to all programming languages, some programming languages, such as C and C++, also require you to declare a function. Next, let's look at the concept of objects. Understanding what objects are is key to understanding object-oriented programming. Object-oriented programming, or OOP, is a programming methodology that is focused on objects rather than functions, which is what procedure-oriented programming is focused on. The objects themselves will contain data in the form of properties or attributes, and code in the form of procedures or methods. The key distinction between the two methodologies is that where procedural programming uses methods to operate on separate data structures, OOP packages them both together so an object operates on its own data structure. Consider the real-world objects in your life, such as your car, bike, TV, or your washing machine, and ask yourself the following two questions. What states can the object be in, and what behaviors can the object perform? When you think about your answers to these questions, you will find that the answers to these questions vary across the objects. More complex objects will typically have more potential states they can be in, and will be able to perform more behaviors. In programming, a software object is similar to a real-world object, conceptually speaking, in that they too consist of states or properties and behaviors or methods. Software objects can be anything, such as a Windows service, a user account, a database table, or a system folder. Objects store their properties in fields, referred to as variables in some programming languages, and expose their behaviors through methods, referred to as functions in some programming languages. In this video, you learned that a function is a piece of structured, standalone, and reusable code that will perform a single specific action. The defining and calling of functions is common to all programming languages. Object-oriented programming is a programming methodology that is focused on objects rather than functions. And software objects consist of properties and methods. Welcome to Introduction to Software Architecture. After watching this video, you will be able to describe what software architecture is, explain the importance of well-designed software architecture, explain how software architecture impacts design decisions, such as tech stacks and production environments, and list several artifacts from software architecture design. Software design and documentation take place during the design phase of the SDLC. Software architecture, simply put, is the organization of the system. Software architecture serves as a blueprint for the software system that the programmers use to develop the interacting components of the software. The architecture comprises the fundamental structures of a software system and explains the behavior of that system. The architecture defines how components should interact with each other, the operating environment, and the principles used to design the software. The software architecture captures early design decisions that are often costly to change once implemented, and a software's architecture addresses non-functional aspects of the application, such as performance, scalability, maintainability, interoperability, security, and manageability. Well-designed software architecture is important for a number of reasons. First, it balances the differing needs of the stakeholders and serves as a basis for communication among team members. Next, the architecture represents the earliest design decisions, and those decisions conflate other coding implementation decisions later in the development process. Also, the well-designed architecture allows for agility due to changing requirements. A well-organized architecture increases the lifespan of a software system, even when implementation details change. Architectural design also guides the choice of technology stacks used for the system. Remember that architecture addresses non-functional capabilities, so choosing stacks that address these requirements is paramount in the design phase. Recall that a tech stack is a list of all the technologies, including software, programming languages, libraries, and frameworks that will be used to create the system. The architects must be aware of the stack's advantages and disadvantages to anticipate development needs. Much like blueprints communicate design decisions to the builders of a house, there are also several artifacts produced during the architectural design phase that are used to communicate the software design to the stakeholders. These artifacts include a software design document, or SDD, an architectural diagram, and Unified Modeling Language, or UML diagrams. The SDD is a collection of technical specifications that indicate how the design should be implemented. It provides a functional description of the software and design considerations, such as assumptions, dependencies, constraints, requirements, objectives, and methodologies. The architectural diagram displays components, their interactions, their constraints, and their confines. It displays the architectural patterns used in the design. Architectural patterns are general, reusable solutions to commonly occurring problems and will be discussed in more detail in an upcoming video. UML diagrams are diagrams that communicate structure and behavior using common programming language agnostic notation. UML diagrams will also be discussed in more detail in another video. But another topic to be discussed in this module as it relates to software architecture includes production deployment considerations. The architecture drives choices about the environment in which the software is released. The production environment is comprised of the infrastructure that runs and delivers the application to the end user, such as the servers, load balancers, and databases. In this video, you learned that software architecture functions as a blueprint and represents the underlying organization of the application. A good architectural design is important because it serves as a basis for communication among team members. Software architecture represents the earliest design decisions, is hard to change once development starts, and accommodates changing requirements during development. Architectural design influences technology stack choices and the production environment. And artifacts resulting from the design include the SDD, the architecture diagram, and UML diagrams. Welcome to Software Design and Modeling. After watching this video, you will be able to compare and contrast the terms structure design and behavioral models, describe Unified Modeling Language, or UML, and its advantages when designing software, and discuss the purpose of an interaction and a state transition diagram. Software design is a process during which structural components and behavioral attributes of the software are documented before it can be developed. One of the key activities of the design process is modeling the software to express its design. This involves creating visual or diagrammatic representations of the bigger software solution and its subcomponents, as well as the interactions between them. This can be done using simple flowcharts or more standardized methods like UML. A software system can be construed in terms of structural elements. Structured design conceptualizes a software problem into well-organized, smaller solution elements called modules and submodules. Structured design stresses organization in order to achieve a solution. A well-structured design should contain modules that are cohesive and loosely coupled. Cohesion means that all functionality-related elements are grouped together, and coupling is the communication between different modules. For a system to be loosely coupled, the modules should be weakly associated so changes in one component have minimal effect on another. And loose coupling is an architectural principle often used in service-oriented architectures and microservices-based architectural patterns, which will be discussed later in the module. This diagram shows a simplified example billing system. Modules are arranged in a hierarchy and communicate with each other. The rectangles represent the modules and submodules, and you can see that billing is the main module and the other rectangles are submodules to the main billing module. In this example, the submodules are insurance verification, submit claim, and output total. The arrows represent the flow of the data in the system. Behavioral models describe what a system does without explaining how it does it. The overall behavior of a system can be communicated through behavior models. There are a number of different UML diagrams that can be used to communicate the behavior of a system. We will discuss two such diagrams, a state transition diagram and an interaction diagram. When developing a complex software system with interconnected modules, it can be difficult to remember the relationships, behaviors, and hierarchies among different elements. UML, which stands for Unified Modeling Language, is a way to visually represent the architecture, design, and implementation of complex software systems. UML is a standardized modeling language that can be used throughout development processes. UML diagrams can be divided into two classes, either structural or behavioral. UML is programming language agnostic, so software developers can readily interpret and apply it to their work, no matter which language they are developing in. There are several advantages of using UML to communicate architecture, behavior, and structure with development teams. The biggest advantage of UML diagrams is that they allow you to plan out features before any coding takes place, which saves time and money. Secondly, the diagrams can be used to bring new team members or developers switching teams to get up to speed quickly. Also, the diagrams can be used to facilitate communication between technical and non-technical audiences more easily. And finally, having a visual representation of the system allows developers to navigate the source code because they can see the relationships among modules. So there are many types of UML diagrams, but generally, UML diagrams can be classified as either behavioral or structural. We will discuss behavioral models next, and then object-oriented design. The behavior of a system can be explained and represented with the help of a UML diagram called a state transition diagram. The state transition diagram is a collection of states and events that describes the different states that a system has and the events which cause a change of state in the system. The diagram shown is an example of a state transition diagram that models a patient going to see a doctor at a clinic. The different states include waiting, testing, and with the doctor. The arrows represent possible transitions from one state to another and names the event that triggers the transition. An interaction diagram is used to model the dynamic nature of a software system. They help visualize objects and their relationships. A sequence diagram, which is the type of interaction diagram shown here, displays the communication between objects with respect to time. This example shows a patient making an appointment in an online portal, and this is another example of a behavioral UML diagram. In this video, you learned that structured design breaks down a software problem into well-organized, smaller solution elements. Behavioral models describe the behavior of the system without explaining how the system implements the behavior. Developing UML diagrams saves time and money by helping developers quickly get up to speed on a project, plan features in advance of coding, and help developers navigate resource code easily. A state transition diagram is a behavioral model containing a collection of states and events that describe the different states of a system and the events which cause a change of state. And finally, an interaction diagram describes how interacting objects communicate. Welcome to Object-Oriented Analysis and Design. After watching this video, you will be able to explain what objects and classes are, describe the purpose of a class diagram, and explain object-oriented design in relation to software architecture. Object-oriented analysis and design, or OOAD for short, is an approach for analyzing and designing a software system when the system will use object-oriented programming languages to develop it. So, before we discuss OOAD, let's learn a little more about object-oriented programming in languages like Java, C++, or Python. At the heart of OOAD are objects. Objects contain data, and they also have behaviors that prescribe the actions the object can take. I could create an object, for example, that represents a patient. And let's say that patient's name is Naya Patel, and Naya needs to cancel an appointment she made. Before creating Naya, however, we must first create a generic version of a patient object. The generic version of an object is called a class. Let's discuss classes next before we discuss more about Naya. Specific objects, also called instances, are created from classes, which are blueprints or templates for an object. So, from our previous example, considering Naya Patel, Naya would be an instance of the patient class. The class contains the object's generic attributes, the properties and methods, but it is only when the object is created, which is called instantiation, inside the code, that these generic attributes are set to particular values. So, the patient class might have a variable called last name, which is a property, but does not specify what that last name is. Last name is just a placeholder until the object is created and assigned a name. And once the object has been instantiated, its methods can be called to make the object perform some action, such as making or canceling an appointment. OOAD is used for a system that can be broken down into objects that interact with each other. In this way, multiple developers can work on different aspects of the application at the same time. As noted earlier, visual UML diagrams can be created that show both the static structure and dynamic behavior of a system. We've seen a couple of examples of behavioral UML diagrams already, so now let's look at a structural UML diagram called a class diagram next, now that we know what classes are. This is an example of a class diagram. Class diagrams are commonly used to communicate a software system structure in OOAD. The class diagram shows how the classes in an object-oriented design relate to one another. Each box represents a class and shows its attributes. Recall that an object's attributes are both its properties or its data and its available actions, called methods. A class diagram also shows the relationships between classes. A subclass is said to inherit its parent class attributes, meaning it has the same properties and methods as the parent class, but also may add additional properties and methods. In this diagram, the nurse, doctor, and technician classes are subclasses of medical personnel, and the specialist class is a subclass of the doctor class. This means that doctors can do anything medical personnel can do, and specialists can do anything a doctor can do. In this video, you learned that object-oriented analysis and design is the process of planning a software system based on the behaviors of interacting objects. Objects contain data, and they also have behaviors that prescribe the actions the object can take. Classes are blueprints for objects, and a class diagram is a structural UML diagram that shows the relationship between objects. Welcome to Insider's Viewpoints, the importance of design and software architecture. In this video, we will hear from experts discussing the importance of design and software architecture in a software engineering project.
Design and architecture are crucial. If you don't know where you're going, how do you know what you need to do now? You always need to know what your program needs to be prepared to handle and the system that it's operating within. If you are running if you're running a bunch of applications that are all co-hosted on the same server, you can make certain assumptions about the ways those services can interact with each other that do not hold.
I also sometimes think of architecture and orchestration. So you can have like a beautiful, really nice sounding instrument, but if it's not in sync with the rest of the orchestra, it's going to sound like a complete cacophonous mess in the end. So you really need to think about the bigger picture, sustainability, whether what you're building actually makes sense in the larger sort of ecosystems.
And every time, if you spend the time to write your code and then you figure out why it doesn't work, you've wasted a lot of time writing that code. Maybe you've learned some things, not a total waste, but you've spent a lot of time that could have been spent moving forward. And so if you can think about those things ahead of time on a project, and then when you write your code, you're reasonably sure that the code you write is actually going to persist and get used, that's generally speaking a better place to be in. So architecture is very important.
Like, there's a lot of talk about its scale, global availability. Often something you build would work very well in a very hyper-local environment, but not work well when it's expected to be used across the globe, or works well for one user but doesn't work well for a million users.
I'm building the service. I need X, Y, Z pieces of data to come into the function that I want to write. Where are those things coming from? How are they getting passed in? Once I have them, what do I need to do with them? What else needs to access this data? And how am I going to get the data to those other parts also? And if you don't have those questions answered, you end up writing a lot of churny code. If everything is on a separate server somewhere in the cloud, or separate physical servers that are just located somewhere different inside your data center, then you have to incur a network hop to go over them. And that takes time. Your page might start timing out, and your customers might get really upset at you for how long things take. And so if you're building something in like a microservice architecture, the way that you load your data becomes much more important than if everything is hosted together on the same server. But maybe the question of who is using my service? How do I know who you are? That can become an interesting question depending on where your services are running, and what mechanisms are available to you to identify people. If you want your customers to log into a website, how are you doing account management? How do you know who that person is and what they're allowed to do? Or if you have multiple services talking to each other, again, how do you know what that service is, what it's allowed to do? How do you make the call between one and the other? How do you transmit data between different parts of your stack? So architecture is very important. It doesn't always have to be super well-defined, super strictly defined, but you need to have some idea of what things do you need, roughly where they're going to live, and what are they responsible for? Those would probably be the three big questions to ask: what, where, and scope of them. So
these sorts of concepts, you have to think about those things when you're designing or architecting a system. You're thinking like 5-10 years ahead too when you're thinking about architecture and design. You're not thinking about just building something quickly and getting it up. You actually want to plan ahead. So I think a lot of architecture and design is thinking about, how many steps, how many years, whatever in the future, what is it going to look like then? What do you need to do to keep growing the system and evolving it? Because you don't want to make gigantic architecture changes that often. You don't really. When buildings are repaired, there's like tiny bits of things get repaired, and then at some point you tear the thing down and rebuild it. And I think that's a similar model applied to sustainable system architecture. You don't want to re-architect and redesign every few years. You want it to last as long as you possibly can.
Welcome to Approaches to Application Architecture. After watching this video, you will be able to describe component-based architectures and service-oriented architecture, explain the characteristics of a component, differentiate between components and services, and describe the characteristics of distributed systems. A component is an individual unit of encapsulated functionality that serves as a part of an application in conjunction with other components. There are 6 characteristics of components. Components should be reusable, replaceable, independent, extensible, encapsulated, and non-context specific. Let's briefly discuss each of these principles. Reusable implies that components should be designed such that they can be reused in different applications. Replaceable means that a component should be easily replaced with another component. Independent means the component should be designed so it doesn't have dependencies on other components. Extensibility entails the ability to add behavior to a component without changing other components. Encapsulation consists of bundling a component's data and methods to hide its internal state so it doesn't expose its specific implementation. And creating a component that is non-context specific involves designing it so it operates in different environments. Data that sets its internal state should be passed to the component rather than included within or accessed by the component. Let's take a look at some examples of components. An API can be packaged as a component if it can be reused across multiple systems and applications. For instance, a component could be an open source API that connects a system to a particular database. A component can also be the interface for a database, called a data access object, that switches the user to a different database without the application knowing about the switch. And a controller is a type of component that determines which other components need to be called for a particular event. It controls the flow of data between 2 other components. Component-based architecture, then, focuses on the decomposition of the design into these logical components. Component-based architecture provides a higher level of abstraction than object-oriented designs. A component-based architecture should define, compose, and implement loosely coupled independent components so they work together to create an application. A service is like a component, also a unit of functionality, but it is designed to be deployed independently and reused by multiple systems. A service focuses on a solution to a business need. A key difference between a component and a service is that a service will only have one unique, always running instance with whom multiple clients communicate. This diagram displays the relationship between objects, components, and services in a layered architecture. Services are made of components, and components consist of objects. A service is a type of component. It is meant to be deployed independently of the overall system. Examples of services include checking a customer's credit, calculating a monthly loan payment, or processing a mortgage application. In a service-oriented architecture, or SOA, services are loosely coupled and interface with each other via a communication protocol over a network. SOA supports building distributed systems that deliver services to other applications through the communication protocol. So let's discuss distributed systems next. A distributed system is a system with multiple services located on different machines that coordinate interactions by passing messages to each other via a communication protocol, such as Hypertext Transfer Protocol, also known as HTTP. Even though the services on a distributed system operate on multiple machines, a distributed system appears to the end user as a single coherent system. A distributed system shares resources such as hardware, software, and data. They are fault tolerant, meaning if a node or a service fails, the system continues to run, also implying that the system may change during execution without service interruption. Multiple activities run concurrently on a distributed system, reducing latency and increasing throughput. Another property of distributed systems is that they are scalable as the number of users increases. The computers running the distributed system do not need to use the same kind of hardware or operating systems. and a distributed system may be made up of different kinds of computers and programming languages. Now, a node is any device on a network that can recognize, process, and transmit data to other nodes on the network. A distributed system consists of multiple interconnected nodes where the nodes are running one or more services in an SOA. Distributed systems generally use one or more of the following basic types of architecture: client-server, 3-tier, peer-to-peer, or microservices. These application architectures and their characteristics will be discussed in another video. In this video, you learned that components are reusable, independent, replaceable, extensible, encapsulated, and non-context specific. Component-based architecture is the decomposition of the system into logical, independent components. Services are made of components, and components consist of objects, and services are deployed independently and can be reused by multiple systems. In an SOA, services are loosely coupled and interface with each other via a communication protocol over a network. And lastly, distributed systems run on multiple services on different machines, and they appear to the end user as a single coherent system. Welcome to Architectural Patterns in Software. After watching this video, you will be able to describe different software architectures, such as 2-tier, 3-tier, peer-to-peer, event-driven, and microservices, and provide an example of each architectural pattern. An architectural pattern is a repeatable solution to a problem in software architecture. Patterns highlight common internal elements and structures of a software system. Different architecture patterns may share related characteristics. In this video, we will discuss 2-tier, 3-tier, peer-to-peer, event-driven, and microservices. However, there are many other patterns that will not be covered in this video. These patterns include model view controller, message broker, blackboard, pipe filter, and controller responder. The 2-tier architecture, also called client-server, is a computing model in which the server hosts, delivers, and manages most of the resources and services delivered to the client. The interface resides on the client machine and makes requests to a server for data or services. This type of architecture usually has more than one client computer connected to a server component over a network connection. A 3-tier architecture, or an N-tier architecture, where there are more than 3 layers, is the most common software architecture. The 3-tier architecture is composed of several horizontal tiers that function together as a single unit of software. A tier only communicates with other tiers located directly above and below it. Related components are placed within the same tier, and changes in one tier do not affect the other tier. The 3-tier architecture organizes applications into 3 logical and physical computing tiers: the presentation tier, or user interface. The middle tier, which is usually the application tier, is where business logic is processed, and the data tier, where the data is stored and managed. The peer-to-peer architecture, or P2P for short, consists of a decentralized network of nodes that are both clients and servers. The workload is partitioned among these nodes. Peers make a portion of their resources directly available to other network participants without the need for central coordination by servers. Resources are things like processing power, disk storage, or network bandwidth. Peers both supply and consume resources, in contrast to the traditional client-server architecture, in which the consumption happens strictly by the client and the servers supply the resources. Peer-to-peer architecture is useful for file sharing, instant messaging, collaboration, and high-performance computing. An event is anything that results in a change of state. An event can be thought of as an action that is triggered by the end user, such as a mouse click or another part of the program. Event-driven architecture focuses on producers and consumers of events. Producers listen for and react to triggers while consumers process an event, and the producer publishes the event to an event router. The router determines which consumer to push the event to. The triggering event generates a message called an event notification to the consumer, which is listening for the event. The components in event-driven architectures are loosely coupled, making the pattern appropriate for use with modern distributed systems. Microservices are an approach to building an application that breaks its functionality into modular components called services. An application programming interface, also called an API, is the part of an application that communicates with other applications. An API defines how two applications share and modify each other's data. APIs can be used to create a microservices-based architecture. The API gateway routes the API from the client to a service, and orchestration handles communication between services. Let's discuss an example for each of these patterns. A text messaging app is an example of a two-tier pattern. The client initiates a request to send a text message through a server, and the server responds by sending that message to another different client. And another example of the two-tier pattern is database clients connecting with database servers. Many web apps use the three-tier pattern. They use a web server to provide the user interface, an application server to process user inputs, and a database server that handles data management. The functions of these three types of servers will be discussed in more detail in another video. Ride-sharing apps such as Lyft and Uber are examples of event-driven patterns. The customer sends a notification that they need a ride from a particular location to another location, and that event is routed to a consumer. Cryptocurrencies such as Bitcoin and Ethereum use a peer-to-peer pattern. Each computer in the blockchain acts as both server and client. Finally, social media sites are composed of microservices. A user has an account, and that account can request different services, such as adding friends, targeted ad recommendations, and displaying content. Architectural patterns are not necessarily mutually exclusive. In other words, two or more of these patterns can be combined. For instance, a three-tiered architecture can also be microservice-based, or a peer-to-peer architecture can also be event-driven. However, not all architectural patterns can be used in conjunction with others. A peer-to-peer cannot also be two-tier because a single machine in a peer-to-peer architecture represents both a client and a server, whereas a two-tier architecture separates the client from the server. It is up to the system architect to determine which architectural patterns the software system should adhere to. In this video, you learned that an architectural pattern is a repeatable solution to an architectural problem. A two-tier pattern has a client and server. Text messaging apps use a two-tier pattern. A three-tier pattern has three tiers that interact with each other. Web apps use a three-tier pattern. An event-driven pattern has actions that are produced and responded to by a consumer. Ride-sharing apps use an event-driven pattern. The peer-to-peer pattern consists of a decentralized network of nodes that acts as clients and servers. Cryptocurrency is an example of the peer-to-peer pattern. Microservices are loosely coupled individual services that behave as a single system and interact with the client. Communication is orchestrated among services, and social media sites are an example. And finally, two or more patterns can be combined in a single system, but some are mutually exclusive. Welcome to Application Deployment Environments. After watching this video, you will be able to list different types of pre-production environments and state their purpose, differentiate a production environment from other application environments, and compare and contrast deployment options. An application environment is the combination of the hardware and software resources required to run an application. This includes the application code and/or binary executables for its various components or modules, the software stack it requires for running the application, such as modules and libraries it depends on, third-party applications and middleware, and the operating system. Any networking components and infrastructure, as well as any physical or virtual hardware, including computing or processing resources, memory, and storage. There are a variety of environment types, depending on the application's stage in the life cycle. The pre-production environments are those platforms that the application resides on in various forms as it gets prepared for production. Common pre-production environments are development, QA, which stands for quality assurance, and staging. The development environment is the platform on which the application is being actively coded, and in many cases, it may just be the developer's workstation. The QA environment, sometimes called testing, is the environment that allows the QA team to test the application's components. The staging environment is the environment that is as close to replicating the production environment as possible, but is not meant for general users. Now let's discuss the production environment. The production environment, often just called production, includes the entire solution stack, consisting of both hardware and software on which the application runs as additional infrastructure components. The production environment is intended for all users. Unlike the pre-production environments, this robust environment must take the application load into consideration because it is the environment intended for general use, possibly by thousands or millions of people at the same time for enterprise-level applications. Production environments must also take into account non-functional requirements like security, reliability, and scalability. This makes the production environment more complicated than the pre-production ones. Now let's take a look at the production environment infrastructure. There are several options for deploying application environments. In on-premises deployment, the system and its infrastructure resides in-house, within the organization's physical location, often behind a firewall. Firewalls prevent unauthorized access to or from a private network. If an organization desires greater security or control of an application and the data in use by that application, it may deploy the application on-premises. For on-premises software deployments, an organization is responsible for the system, hardware, related infrastructure, and maintenance required to run the application. On-premises deployment is usually more expensive when compared to cloud deployment. So let's discuss cloud deployments next. There are 3 types of cloud deployment models: public, private, and hybrid. The public cloud is when you leverage the software supporting infrastructure over the open internet on hardware owned by the cloud provider. That hardware and the associated services are shared with other companies. Public cloud providers include Amazon Web Services, or AWS, Microsoft Azure, Google Cloud Platform, and IBM Cloud. The public cloud is the most common due to its scalability and cost. With a private cloud, the cloud infrastructure is provisioned for exclusive use by a single organization. The software system can be run on-premises, or the infrastructure could be owned, managed, and operated by a service provider. For example, AWS is also a private cloud service provider. The main advantage of a private cloud is its increased security, but it also allows for more flexibility because it can be fully customized. Now, a mix of both public and private clouds working together seamlessly is called a hybrid cloud model. A hybrid cloud potentially optimizes the advantages of both public and private cloud models with regard to cost, security, scalability, and flexibility. In this video, you learned that application environments include development, testing or QA, staging, and production. Production environments must also take into account non-functional requirements like load, security, reliability, and scalability. And application environments can be deployed either on premises on traditional hardware or on public, private, or hybrid cloud platforms. Welcome to Production Deployment Components. After watching this video, you will be able to describe components commonly required for deployment in a production environment, describe the purpose of a firewall and a load balancer, and differentiate between different types of servers. Let's consider an N-tier architecture required to deploy an application in a production environment and represent the infrastructure using a diagram. The top tier is the presentation tier, which contains the front-end client applications. All of the other tiers are located behind a firewall. Firewalls and other components mentioned in this diagram will be discussed in further detail later in the video. Now, the next tier is the web tier, which has a web load balancer that distributes incoming traffic to several web servers. The tier below the web tier is the application server tier. This tier contains an app load balancer or a proxy server that routes traffic to different application servers. And the bottom tier is the data tier that contains the database server. A high availability replica of the database is often used to ensure reliability. Some environments may have additional components or tiers. Also, not all of these components are necessary for every deployment. For example, in some environments, there might not be a need for both application servers in addition to web servers. Now, let's look at these components in further detail. A firewall is a security device that monitors traffic between networks. It permits or blocks requested data based on a set of security rules. It acts as a barrier between networks to block viruses, malware, and hackers from accessing the internal network. The purpose of load balancers is to distribute network traffic efficiently among multiple servers, called a server farm, on a network. Load balancers are used to prevent server traffic overload and are located between clients and the servers. A load balancer determines which servers are capable of fulfilling those requirements in a manner that maximizes availability and responsiveness. Load balancers ensure that no one server is overworked. They manage concurrent requests from clients and return the correct data in a fast and reliable manner. Web and application servers are either software or machines that provide services, resources, data, or applications to another computer program called the client. Servers store, process, and manage network data, devices, and systems. A web server delivers content such as web pages, files, images, and videos to a client. And a web server primarily responds to hypertext transfer protocol requests coming from a web browser, such as a user accessing a website. An app server is a server that runs business logic and provides the application to the client rather than the client running the app on their own machine. Its primary job is to enable interaction between the end user and the server-side application code. The application code represents the business logic that determines how data can be created, stored, and changed, and that logic dictates things like transaction results and what data is written to and retrieved from a database. Next, a proxy server is an intermediate server that sits in between two tiers and handles requests between those tiers. A proxy server can serve multiple purposes, such as load balancing, system optimization, caching, acting as a firewall, obscuring the source of the request, encryption, scanning for malware, and more. And a proxy server can improve the efficiency, privacy, and security of data flowing through a network. Finally, a database is a collection of related data stored on a computer that can be accessed in various ways. A database is usually controlled by software, called a database management system, or DBMS. The DBMS controls a database by connecting the database to users or other programs. The database server controls the flow and storage of data. The DBMS connects the database server to an application so data stored in the database can be retrieved or manipulated by the application. In this video, you learned that common components needed for a production environment include a firewall, a load balancer, web and application servers, proxy servers, and database servers. A firewall is a security device that monitors traffic between networks. A load balancer distributes network traffic among servers. A web server delivers web content, such as web pages, files, images, and videos, to a client. An application server runs business logic and provides the application to the client rather than the client running the app on their own machine. And finally, a database server stores and controls the flow of data through a database management system. Welcome to Insider's Viewpoints, Deployment Architecture. In this video, we will hear from experts discussing important aspects of software deployment.
I think often you need to think about scale, like the sort of just in general, is your system, how many users will your system has, how much data do you expect to flow through it, how much data do you expect to produce and store, how real-time do you need the data access to be, what is your logging story like, do you have privacy concerns, do you need to ensure that data is anonymized, so you kind of, I think, thinking about the scale, the regionality, is it global, is it local, what is your logging, what are your logging needs both for internal and external data analysis, mapping out the data flows. So these are sort of the things I think we start with with design principles.
And in terms of choosing infrastructure, like whether you want to go serverless, whether you want to use a hosted backend, or you're hosting your own, these are all design and architectural decisions that will probably, for your first few jobs, already be taken for you.
What's your system of SLOs, your availability look like, service level objectives, right? So you need to just think about sort of those sorts of things. I think ensuring you like what does a healthy system mean to you? What does a well-running system mean to you? You need to define those metrics up front and sort of have those monitored and watch those as your system lives on, and make sure that you're meeting those objectives and goals and have a plan to mitigate them if they fall below where you like them to be. These days, I think microservices and keeping code as modularized as possible to avoid giant sort of bloated behemoth code bases is really important so that people can move fast and deploy fast.
But what I would say is a critical part of the deployment option is when you look at deployment and integrating your code, testing is fundamental. So I would strongly urge all of you to really pay attention to testing and to use test-driven development, TDD, test-driven development, as a development habit that you inculcate in your life as developers and engineers. It'll stand you in very good stead. I think that's the single most important part. You won't always do it, but you should try and do it as much as you can.
You need to think about whether you want to canarying. There's a canary in a coal mine analogy. So there's a process called canarying where you try to roll out new code and test whether it's going to blow things up or break things. And you want to think about you need to think about how quickly you need to release or not, how quickly you may need to roll back your code or not.
Welcome to What Does a Software Engineer Do? After watching this video, you will be able to describe the types of software that software engineers develop and the technologies that they use. Identify the categories of software engineers and the teams they work in, and describe the day-to-day tasks and responsibilities of a software engineer. Software engineers use their talents in engineering, mathematics, and computing to design and develop software that solves real-world problems for their users. If you're an analytical thinker who enjoys problem solving, software engineering might be the career for you. Software engineers develop a plethora of different types of software, from desktop to web applications, to mobile apps, games, operating systems, and network controllers. They use many technologies to do this, including programming languages, development environments, frameworks and libraries, databases, and servers. There are two categories of software engineer: back-end engineers, also known as system developers, who build the computer systems and networks that front-end applications use, and front-end engineers, or application developers, who are more client-focused. They create the software that users will interact with, such as Android, iOS, and Windows applications, and platform-agnostic websites. Software engineers work in a wide variety of settings. You could work in a team developing off-the-shelf software, bespoke software to meet a specific client's requirements, or internal software for users in your organization. And within your team, you might work on data integration layers, which access and load data from a variety of sources into your solution; business logic, which applies real-world business rules to the data in your solution; or user interfaces, which enable users to interact with your solution. On a day-to-day basis, you might undertake tasks such as taking user specifications and designing new software systems to meet their requirements, writing code and testing that it works as expected, evaluating and testing new software programs, optimizing software programs for maximum efficiency, maintaining and updating existing software systems, documenting code so that other developers can understand it, or presenting new systems to users and customers. And some software engineers, such as DevOps practitioners, also integrate and deploy their code onto the underlying infrastructure. As well as building your own systems, you'll also be testing, improving, and maintaining software built by your colleagues. The responsibilities of a software engineer are as many and varied as the tasks which they undertake. In a junior position, you are likely to start out with a limited set of responsibilities focused on writing, testing, deploying, and documenting code, but as your career progresses, this will widen. And in a senior role, you will likely have primary responsibility for multiple areas of the software solution, including the planning and designing phases. In this video, you learned that software engineers design and develop a range of software solutions. Back-end engineers build the computer systems and networks, and front-end engineers build the user interfaces. Software engineers undertake a range of tasks, from designing and writing new software to maintaining and updating existing software. And as your career develops, you will move from being responsible for one small section of code to many areas of one or more products.
Hi, I'm Shelley, and I work as a software engineer for a startup company in North Carolina. When I arrive at work in the morning, I spend some time catching up on my messages and checking my calendar for the day. Before heading to my daily stand-up meeting, I quickly check the status of my code merge request from yesterday. Great! It's got positive feedback from others in the team and some suggestions from my mentor about improvements I could make. I'll work on those later. During our daily stand-up meeting, each member of the team talks about what they achieved yesterday and what they're working on today. Jonathan, my mentor, gives me some more advice about how I can optimize the code I wrote yesterday. After the meeting, I return to my desk, excited to implement the feedback I've received and continue working on my code. Now, it's focus time, when I can concentrate purely on my project work. I use Jonathan's comments on the merge request alongside the notes that I made during our stand-up to re-engineer a couple of methods to run faster. I also use some of our analysis software to compare timings with the previous version, and, when I'm satisfied that there's a marked improvement, I submit a new merge request to gather additional feedback. I then send Jonathan a message to ask if he can review it later today. After lunch, I'm invited to a meeting where the marketing department explains that they need a new feature to monitor the effectiveness of their campaigns. One of the senior software engineers, Marie, mentions that she's previously developed a React-based front end for a management dashboard that we could easily reuse. I'm tasked with creating a minimum viable product, MVP, for a small team in the marketing department to trial and provide feedback on. I've not used React before, but this is a great chance to get some hands-on experience with it while still making a contribution to the team. Learning on the job and developing new skills is an important part of a software engineer's role. On my return from the meeting, I find that Jonathan has reviewed my code and approved the merge request. He's impressed with the speed of the code and with my coding style. It's really helpful to get regular feedback from more experienced members of the team who can suggest alternative ways of solving problems. I've also received a bug report notification for one of the features I was working on last week. When I review the full report, I quickly spot the mistake and begin fixing it. To check that the fix and the original functionality work as expected, I develop and run a test case for the feature. It passes, so I submit a merge request for my fix and resolve the bug. Now I'm free to start researching React. I spend the rest of the afternoon reviewing the React documentation, watching videos, and reading blogs to give me an overview of React. I then contact Marie to ask for access to the front end she developed so I can review the existing solution. This gives me design ideas and inspires me to start planning my dashboard. On my cycle home, my head is buzzing with thoughts about how the new dashboard will look and the functionality I could provide through it. Tomorrow can't come quickly enough.
Welcome to Skills Required for Software Engineering. After watching this video, you will be able to differentiate between hard and soft skills, describe the hard skills needed by a software engineer, and describe the soft skills needed by a software engineer. Hard skills are the practical skills needed to perform a particular role. So, for a software engineer, these will be the technical skills they need to design, build, maintain, and repair software solutions. Hard skills are learned skills. In the case of software engineering, they are usually learned in a school, college, or university environment, or by studying online courses, diplomas, or certificates. Alternatively, they can be gained from years of experience in the field. Hard skills are quantifiable, so it's easy to measure whether an individual can demonstrate a particular skill and to certify them in that skill. Commonly required hard skills in the software engineering sphere include programming languages, version control, cloud computing, testing and debugging, monitoring, troubleshooting, agile development, and database architecture. Now, soft skills, on the other hand, are less tangible. They are your personal characteristics and interpersonal skills. They're the non-technical skills that are part of your personality and, as such, are harder to define, quantify, or certify than hard skills. Because they're not linked to a particular business, though, they are easily transferable between roles and across industries. The job requirements for any role will be a combination of hard skills and soft skills. So let's look at some of the hard skills that are relevant to a software engineer. Software analysis and design skills are essential for a software engineer. You need to be able to analyze your users' needs through a variety of methods and then design effective solutions that meet those needs. You'll also need to be able to develop those solutions. Computer programming and coding are essential development skills. While some job roles require a specific language and/or toolset, employers will sometimes welcome you with experience in any language but expect you to cross-train into their preferred language. The Coding Bootcamp website, Coding Dojo, states that some of the most in-demand languages are currently Java, Python, C#, and Ruby. An understanding of a variety of frameworks and object-oriented principles are also key skills for a software engineer. While you'd hope to always create flawless solutions, it is likely that at times your code will either not work or not work in the way that you intended. You need testing skills to determine whether your code meets the functional specification of the solution and if it's easy to use. And when your code isn't working as expected, you need debugging skills to work out why. And when your solution is complete, you need deployment skills to distribute it to your users. These could include shell scripting, containers, and continuous integration and continuous delivery or CI/CD tools. You'll also need monitoring skills so that you can review the performance of your solutions and troubleshooting skills to resolve any issues that may occur. So now let's look at the soft skills of a software engineer. Teamwork is a key soft skill. Software engineers work in a variety of teams, some based on the project they're working on and some based on their specific role. If you're practicing agile development, you may also work in small teams known as squads. And you might also work closely alongside another developer in pair programming. Working in teams enables you to take advantage of each individual's strengths, as well as providing opportunities for you to gain new knowledge and skills. You'll need to be able to communicate with a wide variety of stakeholders in your project, from technical colleagues to non-technical personnel. For example, you may need to ask your peers for support and ideas, your manager for guidance and direction, your client for clarification of their needs, and your users how they'd best interact with your solution. Software solutions are often time-sensitive projects, and as such, your manager will be keen that you meet their deadlines. Managing your own time is imperative to ensure that you don't cause delays to others waiting for your work. And with increasing numbers of teams working across time zones, what could previously only seem like a small local delay can create a whole day of lost time for someone located elsewhere in the world. Software engineers need great problem-solving skills to succeed. You need them in the design phase to work out how to create an appropriate software solution, in the development phase to work out the code required to perform the task required, in the testing and debugging phase to locate and resolve any bugs, and throughout the lifecycle of the software to manage any issues that may arise. And when those issues do arise, you need to be adaptable to meet the changing needs of the project. Examples of changes include your client requesting a change or addition to the functionality, your manager requesting you to move on to a different area to meet a looming deadline, or your user requesting an alternative method of achieving a specific task. And finally, you need to be open to feedback on your work. Most software teams use some type of peer review system where peers review each other's code. This helps enforce any corporate standards and improves the code. In a junior role, you'll also likely have a mentor who'll provide feedback and pointers where you can improve. And your stakeholders will provide feedback on pre-release and final versions of your solution. Accepting all of this feedback in an open and welcoming way ensures that your solution becomes the best that it can be and that you progress in your role. In this video, you learned that a combination of hard and soft skills are essential to a software engineer. Hard skills are measurable, learned skills such as programming, testing, and troubleshooting. And soft skills are your personality and characteristics, such as communication and problem solving. Welcome to Insider's Viewpoints, Advice to Future Software Engineers. In this video, we will hear from software engineers discussing their advice to those who are considering getting into the field.
Practice. You should practice all the time. You should learn new skills as much as you can. There are a lot of free resources out there that you can use to help you build new projects. I think the best way to continue working on your craft is to not only learn new things, but also use them to build new projects. Doesn't matter if it's something that's been done before. The point is that you're doing it now, and you're using the tools that you've used to build something new.
The most important thing for my career has been finding a business domain that I am interested in that has what look like not low-hanging fruits, but interesting problems to grapple with. The interesting problems for you are certainly going to be different than the interesting problems for me. But if you narrow down the domains that you're interested in, that can really help tailor both the things that you study, the types of jobs that you apply for. I have other friends where the domains that they're super interested in is like machine learning. Like they're just nuts for machine learning, and so they'll do anything that they can exercise like an artificial intelligence kind of thrust to the whatever business problem it is that they're working on. So like find that general domain and then kind of like dive in on that one.
But don't be scared to fail either. I think the beauty about one of the beauties about software engineering and the way that tech is evolving is there are a lot of opportunities, and there will continue to be new opportunities, and there's lots of movement in the industry. So if you take a job and you really are excited about it, but it ends up not working out as well, you can always, I think, move to somewhere else. There's lots of different types of lots of roles, lots of companies, all that sort of people move around. So don't let one potential failure either mean you give up. I think wouldn't be a failure.
Yes, so my best advice for those looking to get into the software engineering industry is to figure out what role you want to get into, make a list of the required skills for that role, and find free resources to start learning online. So when I was exposed to coding in 2018, after trying a few technologies, I decided that I wanted to be a front-end engineer or a front-end developer. And so I made a list of all the skills that I needed, and I started learning those skills using like free or low-cost resources online.
I think being careful about what's sort of hot and new. There's often, this is more specifically to like taking jobs and how do you find like a good role and fit for you. I know a lot of companies will often sort of market themselves as being, we're working with XYZ new technology. It's super hot, and it's like the latest and greatest, and almost use buzzwords as a way to attract people. Be inquisitive and ask clarifying questions. Be wary in that sense too, or cautious when it comes to some of the buzzwords and new things, and just know what you're getting into.
Don't neglect the job hunt process. Pay due attention to that, because if you just study and don't pay attention to the job hunt process, you're going to get frustrated, because you're going to finish one phase and then have a long period of frustration and self-doubt after that. So if you can do the job hunt phase and preparation sort of in parallel with the latter half of your learning journey, I think you're going to be prepared to hit the market hard when you're ready. And it's just a question of time after that, time and persistence.
Welcome to Insider's Viewpoints, Advice to Women in Software Engineering. In this video, we will hear from software engineers discussing their advice to women in the field or who are considering getting into the field.
Recently, there have been a lot of good positive momentum and diversification of the industry, and making software engineering a more welcoming place for women in general.
So I come from work environments that are, primarily women, and now I'm in a work environment that is primarily men. I think I've had a pretty good experience with my coworkers personally, but in the beginning, it did very much feel like a little bit kind of like you're alone because, you're either the only or one of 2 or 3 women on your team. I would say just remind yourself that you actually do deserve to be there, that you actually do belong. You do belong there. And everybody started exactly where you are. Everybody who started as an engineer and even at your company started and was like, I do not know what's going on, but you're capable and you'll figure it out.
But if you're a software developer at a company, your main job should be software development. And if your bosses or management or other people in the company want you to do other types of work, you should be getting compensated for it. You should have a title that reflects what it is that you do. I have seen this happen a lot where the woman on the team will be the one who cares about diversity, for instance, and so is part of diversity workshops and clubs at the company, and is participating in diverse hiring events and doing all sorts of like extra training around that side of things. And then review time happens, and as a software developer, if you're getting reviewed on code, you need to make sure that you're getting enough of that code in your life. Everyone needs to contribute. Everyone needs to pull their weight. It can't all go on one person.
Join a team that does make you feel like they do support women and want to elevate women and advocate for women. So I think it's very fair to ask directly to, say, a hiring manager, what is your plan for diversity on your team? What types of programs do you or the organization or company have in place to ensure that women are successful, and be willing and open to speak up if there's something that you think is uncomfortable.
It's not all on you to fix if something is broken. There are other people involved, and they also are adults who should be reasonable human beings and able to take advice and constructive feedback. So let them take that advice and constructive feedback. You don't have to do all the changing.
Never be compelled to join a team where you're not feeling good about it, or you think that there's a risk that it's not a welcoming, so ask other people too. I think it's very fair to just ask for those questions.
Don't stay. Don't stay if you don't like it. The company needs you more than you need them, almost certainly. So leave when you can. If something isn't working out for you, leave. You have that ability. And there are companies that have less of that in their culture and less of that in their engineering teams. It can feel rough trying to find it sometimes, but if you do find yourself at a place that is not a healthy, positive, growing environment for you, leave. It doesn't reflect on you. Again, it reflects on the company.
And I know any company or organization that's even remotely taking diversity and inclusion seriously, specifically with regards to with women, will have programs in place to support women, elevate women, and basically there is an eye on that, and as there should be. There's a lot of effort being put into hiring women and getting women into senior leadership roles, which I think is very important.
Figure out what role you want and find free resources to get into those roles. One thing to bear in mind is, as a woman, we are a minority and we're underrepresented in the tech industry. So there are a lot of free or low-cost programs tailored specifically to women who want to get into computing, or women who are in computing looking to advance their careers.
Welcome to Job Outlook for Software Engineers. After watching this video, you will be able to explain why demand is high for software engineers, describe the job outlook for a software engineer, describe what to expect from a software engineering role, and describe the employment options in software engineering. There are various reasons behind the current high demand for software engineers. Almost all industries need software to compete and grow, and this results in a continuous demand for software engineers. Most organizations require applications and websites for their company to function. Some apps and websites are for internal use, while others are used to interact with customers. The Internet of Things is also driving the need for software that interacts with products. This is a need that will continue to expand for the foreseeable future. All types of software programs, from messaging applications to commerce websites to office software, are available in different flavors from different vendors. Whenever one vendor releases a new version of their particular program, a competing company is likely to also update their program, requiring more software engineers to create the new releases, enhance functionality, and add new capabilities. So, the outlook is bright for software engineers. The U.S. Bureau of Labor Statistics predicts a higher than average 22% job growth rate for software developers, analysts, and testers from 2020 to 2030. That's an average of almost 200,000 openings each year in the United States alone. These roles are likely to be across many industries, from mobile application development to health and insurance. There is also predicted to be a large increase in security software due to the increase in computer security threats and cybercrime. Many software engineers are graduates with degrees in software engineering or computer science. However, increasingly, employers like IBM, Google, and Tesla are starting to hire non-graduates who demonstrate the required skills for the role. This opens software engineering up to a wider range of society, ensuring that the cost of obtaining a degree doesn't preclude candidates from the industry. Salaries for software engineers vary significantly with years of experience in the field. As you acquire more experience and become harder to replace, employers typically provide higher compensation. In the USA, salaries range from $90,000 for a junior role through to $120,000 or higher for an experienced position. The average of $110,000 per annum for a software engineer is more than 2.5 times the average base salary across the USA. This, alongside bonuses and benefits such as medical insurance, gym membership, profit shares, and retirement plans, make a software engineering role an attractive proposition. So, what should you expect from a software engineering role? Dress codes are unlikely to be formal unless you're in a customer-facing situation. Hours are often flexible, sometimes around core hours set in the middle of the day. You may occasionally be required to attend meetings or calls which can dictate a physical or online presence at a particular time of the day. And the number of hours are likely to increase as you get near to product release dates, often without any matching increase in pay. The flexibility to work from home varies across employers, but there is no technological reasons why this cannot be done. In fact, some software teams are spread across the globe, working across all hours of the day. Software engineer employers include almost any type of business that you can imagine, from large technology companies such as Facebook, Amazon, Apple, Netflix, and Google, also known as FAANG, to medium-sized software companies that develop specific software and solutions to small software houses and startups. And almost all large non-technology companies, like banks, retailers, and pharmaceuticals, need software engineers for their own internal or external systems. And lastly, most employers will encourage continual learning, whether that be expanding your technical skills or enhancing your soft skills. They're usually keen to invest in keeping your skills up to date so that you can develop the best software solutions for them. Now, in the software engineering world, regardless of your job title, there are different employment options to suit your lifestyle and situation. Employed roles in a company or organization provide stability and a regular income. These can range from an apprenticeship or internship to a part-time role through to a full-time role. In software engineering, more so than a typical job, there is a huge independent contracting market and opportunities in the gig economy. These can range from simple website development to super specialized skills, languages, stacks, and products. In this type of employment, you can provide contract or consultancy services to organizations on a time-based or project-based model, or you can work on a freelance basis, taking on short-term contracts to work on projects that interest you. And many software engineers also code for free as volunteers, contributing to open source projects. This can help you gain experience, enhance your skills, improve your employment opportunities, and enhance your technical eminence. It also makes you feel good by doing something for a cause or community or social initiative that's important to you. In this video, you learned that the high demand for software engineers is due to increasing needs for software, increasing complexity of applications, and a continuing growth of technology. The outlook for software engineers is promising. The role of a software engineer can be flexible and satisfying, and that employment options for software engineers are flexible and varied from full-time employment through to voluntary activities. Welcome to Career Paths in Software Engineering. After watching this video, you will be able to describe typical career paths for a software engineer and identify the likely roles within career paths. A career path in software engineering opens up as you gain experience and attain new skills. Often it heads in one of two directions, technical or management. If you thrive on working with code and solving problems, then the technical path enables you to continue working closely with technology as your career progresses. Or if you exhibit strong leadership qualities alongside the soft skills of a good software engineer, you might progress onto managing a team of software engineers and the work that they do. So let's take a look at a common career path for a software engineer progressing on the technical or managerial path. Remember that different organizations will use different job titles, but the roles will be similar across the board. You're likely to start out in an entry-level position as a junior software engineer or associate software engineer. At this level, you'll be developing small chunks of software to meet agreed client specifications. You'll be assigned a team leader or mentor who will guide you along the way and provide support when you need it. During this phase of your career, you'll be on a steep learning curve, gaining new skills and experience with every block of code that you write. You could then move on to a software engineer position. In this role, you'll be expected to be more independent and be able to break larger tasks down into smaller, achievable subtasks. You may be learning new programming languages and demonstrating an understanding of the software development lifecycle. At this stage, you might be asked to mentor a junior software engineer or take responsibility for a larger part of a project. The next stage of your career could be a senior software engineer position. In this role, you're likely to have involvement across the whole of a project and with an entire code base. You may be asked to mentor software engineers and to conduct code reviews across the team. And from the experience you've gained in earlier roles, you'll be expected to be able to solve a wide range of problems in an efficient way. If you choose to follow the technical path, then your next role might be as a staff software engineer. In this role, you'll work as part of the technical team, developing, maintaining, and extending software. You'll be responsible for ensuring that the software meets customer and user expectations, and that it uses resources efficiently. If you decide to follow a managerial career path, you could become a technical lead. In this role, you'll manage the team of developers and engineers developing the software in your organization. You could be responsible for the entire development lifecycle and report to the project stakeholders. Continuing along the technical path, you might progress to be a principal engineer or technical architect. At this stage, you'll be responsible for the architecture and design of a software solution, as well as the development of it. You'll be expected to create processes and procedures for your team and provide technical direction. On the managerial path, you could become an engineering manager. In this role, you'll ensure that the entire team is appropriately supported and encouraged to progress in their careers. Becoming a director of engineering could be the next stage in the progression of your career. It is a strategic and technical role. On the strategic side, you'll determine priorities for the projects within the company, identify hiring needs, and define long-term goals. On the technical side of the role, you'll be involved in defining new projects, specifying requirements, and overseeing the project. The lead of an organization's technology arm is likely to be the Chief Technology Officer, or CTO. In this role, you oversee all of the research and development in the company. You'll also monitor the company's systems and infrastructure to ensure that it meets your needs and budget. Even at this level, you'll continue learning. As technology evolves and new products appear on the market, you'll be responsible for deciding which ones meet your business needs and could give your organization a competitive advantage. Of course, not everyone who starts out as a junior software engineer follows these traditional software engineering paths. But you'll find that the skills you gain will benefit you in a wide variety of other roles. If after working on client projects for a while, you decide that you prefer interacting with the clients to writing code, you could transition into a technical sales or customer support role. If you enjoy coding but find working with numbers and data is more appealing, you could transition into a data engineer or data scientist role. And if you find that the data side of your new role is your passion, you could move on to become a database administrator or database developer. And if you enjoy finding and fixing bugs, you might transition to a software tester role. IT is a vast field with an abundance of opportunities across many skill sets. So starting your career in software engineering is a great choice, even if you use it as a stepping stone to move to other technical or leadership roles in the future. In this video, you learned that a career in software engineering is likely to follow a technical or managerial path. At each stage on that path, you will take on more responsibility and a wider range of tasks. And starting out as a software engineer enables you to take on an array of other options at any stage in your career. Welcome to Software Engineering Job Titles. After watching this video, you will be able to list commonly used job titles for software engineers and identify the primary duties of and skills needed for these roles. Job titles such as software engineer and software developer are very broad and can be used to describe a spectrum of roles. As well as these titles, you may come across other titles related to specific subdomains in software engineering. While individual organizations might use company-specific job titles, you'll find that most fit into one of the more generic titles. Types of software engineer roles include front-end engineer, back-end engineer, full-stack engineer, DevOps engineer, software quality assurance engineer, software integration engineer, software security engineer, mobile app developer, and games developer. Front-end engineers focus on developing the user interface, or UI, of a software solution. They're also sometimes referred to as UI developers or web developers. In this type of role, you're responsible for the visual design of the software, including the layout of UI elements and the overall aesthetics of the application or website. It's important for a front-end developer to understand how users interact with software and the principles of user experience design. You'll also need to understand how objects and code run differently on different operating systems, devices, and browsers to ensure that your solution works on the user's chosen system. Key skills of a front-end engineer include web development languages and UX and UI frameworks. Back-end engineers focus on the business logic of a software solution. In this type of role, you're responsible for the core logic of the software implementing functionality to perform tasks such as accessing data and databases, logging information, and caching systems by using application programming interfaces or APIs. You'll also be responsible for ensuring the scalability and performance of the solution. Key skills of a back-end engineer include programming languages, application frameworks, web servers, app servers, and load balancers, databases, and deployment and containerization tools and technologies. Full-stack engineers work across the whole software solution. In this type of role, you're able to create both the user interface and the back-end functionality of an application or website using the skills of both front-end and back-end engineers. Key skills of a full-stack engineer include web development languages, programming languages, UX, UI, and back-end frameworks, web and application servers, databases, APIs and web services, and deployment and containerization tools. DevOps, or Development and Operations, aims to deliver the software in an agile manner by combining software development and IT operations. DevOps engineers apply agile processes and methodologies to streamline their product development, improvement, and maintenance, as well as transcend the boundaries of the traditionally distinct development and operations teams. In a DevOps role, you need familiarity with both front-end and back-end technologies. The skills, technologies, and products that a DevOps engineer is likely to use include source code management tools, programming languages and frameworks, scripts, and deployment, containerization, and monitoring tools. And depending on the actual job posting, you might use alternative products and services, but they will be of a similar nature to those shown here. Software quality assurance engineers, also referred to as software QA engineers or software test engineers, test, review, assess, and write software to validate the quality of an application. In a QA role, you'll develop automated tests, tools, and procedures to test the functionality of software solutions. You'll use bug tracking software to log any errors you discover and report them to the software development team. The key skills for software QA engineers include programming languages, shell scripting, bug tracking and issue management tools, testing automation tools, and specific software stacks depending on how the application is deployed. Software integration engineers write code to integrate software into hardware products, enabling smart devices and the Internet of Things products. In this role, you'll use programming languages and frameworks to program hardware, such as consumer devices, home security systems, electronics, and other interfaces. The key skills for a software integration engineer include programming languages and proprietary technologies, frameworks, and toolkits. Software security engineers, sometimes referred to as white hat or ethical hackers, work to find security flaws and vulnerabilities in software. As a security engineer, you'll create systems, methods, and procedures to test software solutions and exploit their security weaknesses so that they can be fixed before the solution ships. The key skills for a security engineer include programming languages, reverse engineering, shell scripting, tools for vulnerability and penetration testing, and network security and encryption tools. Mobile app developers design, develop, and implement software solutions for mobile devices, such as smartphones and tablets. You'll use web skills to create front-end apps, as well as learn the various different platforms to write the back-end code interacting with the specific type of device. The key skills for a mobile app developer include mobile operating systems, web development languages, and programming languages, as well as web services and technologies. And games engineers write gaming software for a wide variety of devices, from PCs to smartphones to web browsers to game consoles. As a games developer, you'll work alongside graphic artists, sound technicians, and game designers to create the code used in games. In this video, you learned that there are many different job titles under the umbrella term of software engineering, each of which has specific duties and responsibilities and requires a specific set of skills. Welcome to Insider's Viewpoints, Career Pathways, and Continuing Education in Software Engineering. In this video, we will hear from experts discussing how they became software engineers, their education, and their background.
So I have a non-traditional path into software engineering. My bachelor's degree is in social work, and I worked as a social worker for some time. I was introduced to coding via social media. Randomly on social media, I was scrolling in December 2018, and afterwards I kind of fell down the rabbit hole of learning how to program, and I decided to go to a 10-month-long, very intense coding bootcamp to make the switch into software engineering. And so one thing I have learned over the past three and a half years is that your career doesn't have to be linear, and your career doesn't have to look like anyone else's.
So I just picked computer science. I loved math. That's the only thing that I think really drew me to computer science was, if you love math, apparently you'll love computer science too. So I think some of the most successful engineers that worked for me or I've worked with come from backgrounds, not even sort of like mine either, people with non-technical backgrounds who picked up coding on the side. There's so many folks who come from or English majors or philosophy majors or bio, whatever it is, because I think there's this, you can learn all these skills and become a really strong engineer without having gone to a 4-year college or more for computer science specifically or another engineering role.
In college, I ended up taking applied math. I did applied math as my major. I always wanted to work on things that had a practical application, which is why I went into applied mathematics rather than pure mathematics anyway. Yeah, so I did that research program, and as part of that program, we were writing simulations using MATLAB, actually. That was a fun time. So we were writing simulations using MATLAB, and I realized I enjoyed that part more than I enjoyed the mathematical research part of it, and that's kind of what kicked it all off. It's like, oh, computers are a lot of fun. So I ended up graduating college with an applied math major, a computer science minor, and then I've been taking computer science jobs ever since then.
So I received a Bachelor of Fine Arts, actually, so not anything tech related. And I worked in education for a few years. I ended up as an art teacher, and it was during that time that I decided that I wanted to switch paths because I wanted a little bit more freedom with my job, more flexible schedule. I wanted the opportunity to work remotely. So I decided to take a class to see if I would like it at a community college near my house. And I really, really loved that class. And at the same time, kind of just watch videos on Udemy and YouTube and teach myself some things that I wasn't learning in class. I took 32 credits at the community college level. And then after that, I did apply to graduate school. While in grad school, I received an internship offer at my current company. I did a summer internship, and directly following that, I started full-time.
Next, we will hear from these experts regarding how they maintain their skills and keep up with the continuous technology evolution.
I follow people on Twitter who talk about emerging technologies and new technologies. I also subscribe to this newsletter called TLDR, and they pretty much just surmise everything that's going on in the tech industry. That's what I like to do to keep up to date. And I also take various courses on things that are interesting to me.
Yeah, and I think just carving out time to learn, whether it's within your, often companies will give people some amount of time to for personal development and growth, which can mean taking courses to learn new languages or frameworks.
I've found that I learn best if I have a project that makes me need to learn the thing. So I started with Googling. Like, honestly, Reddit threads frequently are the best places to find out about like what are the popular and new technologies these days. If you just search on Google for like best website framework Reddit 2022, you'll find numerous posts of people debating the pros and cons of different types of frameworks. And then actually another very important thing is debug it. Attach a debugger, put in print statements, do everything you can to be able to inspect the flow of the code that is getting run. Knowing how to debug is about almost equally an important skill as knowing how to write the code.
The way that I kind of keep on top of everything is reading documentation. I have really great coworkers who are always also in the know of like when things are updated, when languages are updated, when to use new technologies. So they help me out a lot there. And we also get Udemy for free, like Udemy Business for free for all employees, which is a really great way to learn new things and also stay on top of new technologies that come out.
Welcome to Software Engineering Code of Ethics. After watching this video, you will be able to state each of the 8 principles in the Software Engineering Code of Ethics and explain each of the 8 principles in the Software Engineering Code of Ethics. The Joint Task Force on Software Engineering Ethics and Professional Practices developed a code of ethics outlining their goals and standards for software engineers engaged in the design and creation of software. The task force was formed by the Institute of Electrical and Electronics Engineers Computer Society, or IEEECS, and the Association for Computer Machinery, or ACM, in order to recognize the prominence of computing in global commerce, government, and society. This IEEECS-ACM Joint Task Force championed the need to hold software engineers accountable so that the present and future status of the field as a beneficial and respected profession is maintained. The Code of Ethics consists of 8 principles that pertain to the specification analysis, design, development, testing, and maintenance of software and are dedicated to serving the public interest. These principles are intended for anyone who is in or related to the profession and includes engineers, mentors, instructors, managers, students, and policymakers. Here we will summarize each principle. However, the full text of each principle and its additional clarifying clauses can be found on the IEEECS and ACM websites. The principles in the Software Engineering Code of Ethics focus on the following topics: public, client or employer, product, judgment, management, profession, colleagues, and self. The public principle comes first because it is expected that software engineers should act primarily in accordance to positively affect the public good. This includes accepting responsibility for their work with regard to safety, fairness, accessibility, and integrity. Next, software engineers should act in the best interests of both their clients and their employers. They should act honestly and be forthright when it comes to unethical actions such as plagiarism or illegal activities. They should seek consent where necessary and appropriate and honor confidentiality. The third principle relates to the product under production. Software engineers should seek quality while keeping in mind cost and timelines. Now, this next principle outlines how software engineers act with integrity and independence in their professional judgment. They are expected to maintain objectivity and honesty when working with the software and relevant documents they are involved with. Software engineers should not engage in any inappropriate financial activities, such as bribery and double billing, nor may they accept duties that create a conflict of interest. Software engineering managers and leaders should also behave in a manner consistent with these principles where it applies to them and those they manage. They should work to minimize risk and employ security procedures. And managers and leaders should also work to ensure realistic expectations of their staff, provide just compensation, and procure intellectual property rights whenever appropriate. The profession principle describes the duty of software engineers to protect the reputation of the profession by acting with integrity and not elevating themselves at the expense of others. Software engineers should let managers, employers, and clients know they intend to act in compliance with this code of ethics and express concern over violations of the code. Similar to the profession principle, software engineers shall treat their colleagues with respect and fairness. They should encourage their peers to comply with this code of ethics and not take credit for the work of others. The final principle, focused on the software engineer themselves, reminds software engineers about the importance of lifelong learning and professional development. They should endeavor to create quality software and strive to conduct themselves in a professional manner. It should be noted that this code of ethics is not a replacement for conscientious decision-making and common sense, but it can be used as a supplemental guide. Knowing when and where to apply these principles will always be up to the discretion and wisdom of the individual. In this video, you learned that the Code of Ethics serves the public interest to hold software engineers accountable in the analysis, design, development, testing, and maintenance of software. And the 8 principles in the Code of Ethics are public, client or employer, product, judgment, management, profession, colleagues, and self.